Hey everyone, do we have sound? Alex, how are we doing? Hopefully we have sound. It looks like we have sound. Tell me everything's going all right. I made some changes, trying to get things all fixed up. Do we have sound? Do we have audio? Hey Nicole, good to see you here. Let me make sure we're on top chat, live chat. Yes, I can hear you. That's awesome. Woo! Getting a little bit scared there. We're going to turn on MuBot here. MuBot's waking up. Something's going on with my Stream Deck. We had to make some changes, getting things fixed up. Thank you everyone for waiting. All right, saying nope, your openings aren't there. Well, we'll worry about that later. Roy, KP, good to see you. Ella, good to see you. Audrey, good to see you. Joseph, good to see you. Everything's loading up. Stream Deck's being weird. Let me load up Stream Deck. I was going to play people in opening because maybe everyone hasn't seen it, but we'll get started here in just a second. YouTube is muted. No, I do that all the time, especially if you have like two things open. Alex, let's throw everyone 1,000 points. If you're here, we give out some big points. Chase, great to see you here. Good to see everybody. Oh, okay, is it working now? Well, we'll worry about that later. I just reset my computer, and for some reason, the things aren't working like my openings. I go to my openings page. I'll have to disappear, but you get to see all the inner workings of Stat 201 right here. I was going to play an opening, and it's like, nope, you can't see it. It shows that these are broken. Have crazy studio opening on. But we'll worry about that later. Oh, now Marvel's thing isn't working. This is weird. Okay, the Marvel button's not working. Why? Oh, please, everything don't be broken. Well, that's... Okay, can I reappear? Oh, I can't reappear. Wow, something's weird. Well, 1 second. I'm going to have to reappear. Just a second. Let me restart the Stream Deck. Sorry, everybody. We're going to restart the Stream Deck here. So, 1 moment. Just restarting Stream Deck and seeing if this fixes the issue. Okay, Stream Deck's restarted. It says I'm here. That says Brian's here. 2 seconds. I got to reappear. I have to do this myself now. Oh, no. I think you're about to see a little behind the scenes. I think I've got this on camera 1. Okay. What is going on? Let me bring the Marvel back up. All right. We're going to get started here in just a second, but Stream Deck is just being really weird. If you're wondering, usually we don't have all this craziness. Okay. Well, maybe I shouldn't say things aren't working. It turns off, but it doesn't turn back on. All right, well, we're going to midterm. Well, everything's going crazy. But how is everyone doing right now? Who wants to start talking about some... let's talk about some BAS 320 final. Who's in for that right here? Who wants to talk about BAS 320 final? How does that sound, everybody? BAS 320 final. Audrey wants to talk about it. That sounds like good to me. Nicole wants to talk about it. Micaiah wants to talk about it. Good stuff. I don't know what I did to everything. I was trying to fix the issues of the random things we have. We need it. Well, that means it's time for it. Does going to the main screen work? Let's find out the hard way. Here we go. It does. We can go over to the main screen. Well, that's awesome. I might not be able to reappear, disappear. I might be reconnecting some wires later. Who knows? My exam is today. Well, let's start this out. Ryan, what questions do you have? Lots of stuff to cover right here. What do you want to talk about first here? We're going to take some notes. Let me pull up the notepad. Sorry if I break things. I don't even know. Okay, we're going to see. Let me see if my buttons aren't going to work. I got to remember today, I don't got buttons. I don't got fancy buttons. What should we talk about here to start? It's your call. We're 5 minutes in. What's the first topic of the day? You name it, we talk about it. What topics are you thinking about? All interpretations. Let's talk about interpretations. That's some great stuff right there. Okay, this is at 5:30. We're talking about interpretations to start. Okay. So when it comes to interpretations, we're talking about interpreting the coefficients. Good to see you, Mary. Oh, we'll do some AIC. Let me put AIC on here. Okay, AIC. We'll talk about AIC in just a little bit. So we're going to talk about interpretations to start. What do we interpret in models? Who can start us off with this conversation on what do we interpret in models? I'll start making a model right here where you think about what we interpret. And let's say our first interpretations right here. So what do we interpret in a model? I mean, there's a lot of things, but when we talk about a descriptive model, we're mainly talking about, interpreting the what's of the model. Coefficients, KP, can I still give out points? Yes, I can. Great job, KP, right there. We interpret coefficients. So let's try to interpret the weight explained by horsepower. These are coefficients. These are data sets you already have inside of R. Like I know it says there's no data up there. But interestingly enough, the empty cars data set is a data set that's always inside of R. It's kind of like a preloaded game inside your computer. So you always have access to this data set by default. It's kind of hovering in the background, even though you can't see it. So we're using the column, the weight of a car in tons, let's say, and horsepower in terms of how many horses. So when you think about this, there's going to be two coefficients in this simple model. So a simple model has an intercept and a slope, B1 coefficient. Does everyone understand what's going on? What do we call the intercept coefficient by just statistical notation? Think of it, it doesn't go within X. There's the first X in your model, sometimes a second X, a third X. What is the intercept called in notation? When you think about how we call like the first X gets B1, great job, Alexander, right there. We call it B0. And these mean estimate. They're not beta. Beta is the true intercept, the true slope. B is the estimate, which comes from sample data. So now that we know what coefficients we're going to be talking about here, we can make a summary of this model. And please slow me down or ask questions if you have it. This is where we wanted to get to. And weight is in tons. So let's see. Is there another one? I hate small decimals. Well, you can because you're typing it out. I'll have to say it. Now be very careful. Let's start with the intercept, which is the easier one. Hey, Zachary, good to see you here. Let's do the intercept, which is a little bit easier. The intercept, how would you interpret that? Now, see if you can get it before I say it. Try typing it in chat. That's always how we practice right here. If you type it in the chat, it's just good practice to be like, how do I interpret that intercept right there? Meebot's always so friendly. You can get him stuck in a loop. How do we interpret the intercept? Remember, we're predicting weight of cars. You can also use the output to help you understand what you're predicting. Remember, it's y tilde x. So this is the y variable of interest, the one we're trying to explain. You won't see it down here in the x output. So how would this be talked about? We're talking about cars here, remember? How would you interpret it? And I'll interpret it in a moment, but let's try to get 2 or 3 people typing in the chat. You're going to be typing it out on your test, so this is a good time to be like, could I interpret the intercept? How close would I be? Would it be to something we'd be like, yeah, that's great interpretation. So what do we have right here? Remember, the intercept with horsepower at 0, the weight of a car is expected to be, boom, Chase, right there, you got it. When horsepower is equal to 0, we expect the weight to equal this in tons on average, exactly. And then great words right there, Ella and everyone. You want to make sure you put in words like expect. If you think about visually what you're talking about a prediction line. Oh, we don't have red class loaded up. You don't have, and I'll put this up here because I'll probably post this, or I'll throw it on the Discord or something. And so if we visualize this model, you can see what we're talking about. I might not blank myself out anymore because, yeah, it's super angry. Remind me, everyone, I'm not going to be removing myself from the screen. Something's going on with the Stream Deck, and I don't know what it is, but I'll have to do things like this. I can't remove myself lest I have to go over there to bring myself back. But if you look down here, you can't see the intercept. Be careful. It's just the graph doesn't go out that far. But this is the predicted or expected, Micaiah, great work right there. The predicted or expected horsepower of a car when, predicted or expected weight of a car, that's the y-axis. Predicted or expected weight of a car when horsepower is equal to 0. And it's best to think about it mathematically too, because in simple mathematics terms, if you write out the model right here, you'll see that your model is going to be, let's write right here, weight equals 1.838 plus 0.009401 horsepower. And then when you think about solving this, you're literally interpreting what you do when you solve it by talking about the intercept. To solve for the intercept, just do what? To solve for the intercept, just do what to this equation? Because we've written the equation with the coefficients, intercept plus coefficient times x right there. So there it is, the intercept plus coefficient times x. If you want to solve for the intercept, the x-intercept, just plug 0. And so if you look at the interpretation Makai just said right there, when horsepower is equal to 0, we estimate, talking about the prediction we're making, that the car's weight will be, they just mathematically do it. Just there you go. There it is. So kind of makes sense right there to say when horsepower is equal to 0, we predict or we expect the weight of a car to be equal to this in terms of tons. And so just think about what you're doing mathematically. Great job right there, Ryan. So if you plug it in and think about what you would tell somebody you're doing mathematically, you can usually interpret the intercept. If it's a multiple regression, all of the x's are 0. But now we get to the harder ones. Usually there's mistakes when we interpret the coefficient of an x. Reason being is we don't want it to sound like cause and effect. There's some bad words in this class. Does anyone know any of our bad words? Will, cause, accept, prove. We don't talk about those words in this class. We don't say will, cause, accept, or prove. Those are words we don't like. We don't say this is this. We say we estimate it. You want to give a little bit of like uncertainty in statistics. And where do you see your uncertainty? We're about to interpret a coefficient, but where do you see your uncertainty in the estimate of that coefficient? We're talking about this output right here. Make sure we understand what we see, because the coefficient is just an estimate. Literally says that. And your uncertainty is where in this? Like, where's your uncertainty in it? The standard error. So helping us understand, great job, Nicole, right there. The standard error is like, your friend says, I'll be there at 4, but I might be about 5-10 minutes late. We give a number. It might be about 5 minutes late. You say dinner will cost about $30, but it might be off by about 5. This is I might be off in my estimate by about this amount. So the standard error is a measure of uncertainty. We can work more with that later, but just understanding that this is an estimate, we're not saying it is true. It's kind of what we expect. So who can interpret the coefficient of horsepower? Take a moment right here. You know I want you to do it before I do it. Take a moment and interpret that coefficient of horsepower. Simple. So let's put it right here. Whoops. Sorry. Can't see it now. Simple linear model coefficients interpreted. Who's got it? Colin, great to see you here. For every change, little cause and effect right there, Alex. Good attempt, Alex. Alex, 100 points. Good attempt. With two cars that differ in horsepower by 1 unit, we expect them to differ in weight by 0.009401, where the one with more horsepower is expected to weigh more. And Alex, we're throwing 1,000 points for Alex, because Alex went first right there. Alex, great job. And so we're going to practice this right here, and great job, everyone writing it out. So let's take a look. I think Morgan has it too. Two cars that differ in their horsepower by 1 unit are expected to differ in their weight by 0.00941 units, where the one with the higher horsepower is expected to weigh more. Exactly. And Joseph looks like interpretation 2. Two cars that differ in horsepower by 1 unit are expected to differ in weight by 0.009 units, where the one with the higher horsepower is expected to weigh more. And the best way to think about this, I'll do another model here in a moment that'll really point to this. And let's write out this interpretation and then see why we use this interpretation. Especially in this class. And Alex, great work right there. Some big points. I promise you, everyone who's wanting to get points is like, yes, thank you for the points. Because first answer, jumping out there, taking some chances at it. Two cars at different horsepower 1 unit are expected to differ in weight by 0.09 units, with the higher horsepower having yeah, and then since you said expected, yeah, as long as you put in the expected and then you don't say will or something, yeah. That's great right there, Alexander. Excellent work. Okay, so 2 blanks. So you have to give the context of what you're talking about. 2 blanks that differ in X by 1 unit. There we go. Are expected to differ in Y by B1 units. And then higher, lower. There we go. Where the larger X is expected have the higher/lower Y. Okay. That's about as formulaic as I can make it. You just talk about what you're talking about. And I want you to think about this. Like, this is where I hope it starts to be like, oh, that's why we do this. Let's talk about joining the NBA. So who wants to be in the NBA besides Brian? Because we're going to figure out the magical formula to join the NBA. Okay. This is how we can get in the NBA, according to the bad interpretations. Take a moment and give me a bad interpretation of weight right here. Don't give me the good interpretation. This is the no, don't do this. This is our reminder. Don't do this on the test, because if we use some interpretations that you might see elsewhere, it's going to sound a little bit, are there different coefficients for multiple regression? That's what we're going to start to get into here soon, Chase. This is just simple quantitative interpretations right here. We're starting out with the simple, and then we're going to build on top of that, and we're going to get to some more complex interpretations, but it all starts with the basics of interpreting just a regular coefficient. So we're always going to say two blanks that differ in. You're going to see the same structure throughout, but we're going to build on top of that in layers. But what would be a bad interpretation of weight right here? Like, think of like a stat 201. Sorry, stat 201. But my Pearson has us do it a certain way. What is it bad? It's KP knows what's up right there. KP 100 points. Yep. Throwing a little otherwise equal. So what would be a bad interpretation of this? It's not going to make much sense. That's like, I don't know about that, Brian. I don't know if it works that way. I don't know why your coffee has grounds in it. I don't know why you're showing the class. Tiny Brian. Well, Tiny Brian's got a pathway to the NBA. What does Tiny Brian need to do? He won't be Tiny Brian much longer. If we use bad interpretations, who's got me on my bad interpretations right here? So we're trying to remember how to not interpret things right now. The things we don't do here. Bad interpretations. We don't do that here. For every 1 unit increase in weight, height. Oh my God. Nicole, that interpretation is so bad. We have to give 1,000 points. Nicole hit the nail on the head. I died a little bit typing that out. For every 1 unit, please do not. See, some links the review and they tell their teacher, Brian said this. For every 1 unit increase in weight, height will go up by 0.07 inches. So what's the pathway to the NBA? We're going to Cookout tonight. Then we're swinging by In-N-Out. We got one in Knoxville now, if you didn't know. Someone's freaking out and wanted to go over there. And then we're swinging by some Five Guys, picking up some Pizza Hut just to eat. Because for every 1 unit increase in your weight, which is a pound increase, let's say, for every pound increase, your height will go up, getting those LBs. So if someone says, got to put on some pounds, they're just like, yeah, go eat and you will get taller. But what's the right interpretation? And then I want us to think about it and what we're saying. Just think about two people in the world. Two people. Imagine these two people. Two people, and maybe they differ by, let's say these two people differ by 10 pounds. If two people were to differ by 10 pounds, we'd expect the person who weighs more to be what? Like, let's say we have two people. Weight causes height. We have two people. Good to see you here, Terry. We have two people, and they differ by 10 pounds. I'm using 10 as my unit different change. Not change, but difference in individuals. Two people who differ by 10 pounds. Well, then I'd expect them to differ in their height by what? I have two people who differ in their weight by 10 pounds, person A, person B. And then I would expect them to differ in their height by what? Let's write out the equation. If you don't know the answer yet, let's write out the equation. The equation would be, remember, we're predicting height equals, plus, it's a positive coefficient. That would be 100 pounds, Nicole. Good job for 100 points right there. That'd be 100 pounds. 100 pound difference, the expected difference between individuals would be 7.3 inches. 10 pounds, 10 pounds, 10 pounds, which you're right on the right track with that, Nicole. So if we had two people who differed in their weight by 10 pounds, the expected difference would be 0.73. Great job, Jesse, right there. And does that make sense? What you're doing is you're just plugging in like 140 and then 150. So the unit difference there is 10. And that's the difference you're seeing. Like, you're seeing they differ by this much. So we would expect this much of a difference. And when you think about it visually speaking, that's what the model, the red line here, is showing you. The red line is showing you the predicted differences between individuals who differ by this many units. Now, the coefficient itself is for a 1 unit difference. We can talk about a 10 unit difference by multiplying it by 10. I know, right, Nicole? Two people that differ in weight by 10 pounds are expected to differ in height by 0.73 inches, where the one with more weight is expected to be taller. Yeah. If I tell you I have a friend who weighs 80 pounds and I have a friend who weighs 200 pounds, who do you expect to be taller? And it almost, I'm thinking about my friend John and myself. That'd be we expect like a 9-inch difference. But just think about that. I have a person who's 80 pounds and 200 pounds. I'd expect the person who's 200 pounds to be taller. And you could literally take this right here and figure out the expected difference, about 9 inches. You'd expect about a 9-inch difference. That's what this model's talking about. It's predicted differences in height between individuals. Every dot here is an individual. But look, not everyone follows the relationship. It's a predicted or expected. We're not saying you will be taller. Got some tall people here, got some shorter people here, got some shorter people here, and taller people with the legend blocking it. So we are not saying you will be taller. We are just saying we expect you to be taller. And keywords like that are very important. This person here is quite tall, and they're only 75 pounds. I don't know if they entered their data in properly, but they reported being very tall and very light. But you will see there is a relationship that we expect or we would predict or estimate between individuals who differ. And that's how we talk and be very exact. We don't want to make it sound cause and effect. So that is how we interpret a simple coefficient. And the reason we focus so much on that right now is because we're right about to build on it. Let's do the next easy thing. The next easy thing is sticking with only quantitative variables. So now let's do quantitative interpretations in a multiple model. So when I say multiple model, what does that mean? If I say multiple, what does that mean? I saw there's a question here. When I say multiple, what does that mean? I'm taking the note in the chat. What up, Brian? Barrett, good to see you here. Check those points. I think you're saying good to see you, Barrett. Might hang out and get some more points. Multiple X's. Barrett, you have jumped into the world of multiple regression. More than one X. That's when we say multiple regression right here. Simple. Simple is just one X. Okay, so let's do a multiple. Let's take our height weight model right here. I think KP already knows what to do. KP, you're ready to go. Let's go here and do desired weight. Desired weight. So now we have two X's, which might share some multicollinearity. More on that later. And let's take a look. Ooh, this is interesting. What do you notice is weird about the coefficient of weight now? What do you notice is interesting about the coefficient of weight now? You might never have expected this. This is the multiple world, and this is why I wanted to use these ones. It's negative, right? So wait, Brian, you're telling me people who weigh more are shorter? People who weigh more are shorter? Brian, I can look at the world right now. I just looked at that 200-pound person and that 80-pound person, and the person who weighs 200 pounds is taller. Brian, your stats is stupid. Don't be so mean to me. Because there's an important thing we acknowledge in this. There's an important thing we acknowledge. KP pointed out earlier, anytime you do a multiple regression, you need to add in a phrase. So this is needed in multiple regression. What do we add in? KP was saying it earlier. What do we add in that says, hey, we're in the multiple world here. We're not just talking about weight. Two otherwise identical. And so you can put it in a lot of different spots. You can say two people who are otherwise identical or two otherwise identical individuals, two people who differ in this but are otherwise identical, as long as you're adding in the phrase are otherwise identical. Many ways to add it in right there to say two people who differ in this X we are interested in but are otherwise identical. So let's grab everything we just said a moment ago, and then literally the addition, which is so very important right here, is the inclusion of the phrase are otherwise identical. Make it kind of clear that this is the addition right here. You have to say, but they are otherwise identical. Because if we interpret this as a simple coefficient, it would be two people who differ in their weight by 1 pound are expected to differ in their height by 0.03 inches, where the person who weighs more is shorter. But what we should see right here is two people who are otherwise identical. That means we have a Brian who wants to weigh 180 and another Brian who what? Like, or another person who what's? If we're interpreting weight right here, we'd have what? A person who wants to weigh 180 and another person who what? Now remember, we're interpreting weight. So if we say they're otherwise identical, then we'd have a person who weighs 180. Well, so we'd have a person who weighs 180. Oh, excuse me, I misspoke right there because they're both like weight. A person who wants to weigh 180 and another person who wants to weigh 180, but these two individuals differ in their weight by 1 pound. Does that make sense? A lot of weight coefficients right here, so a little confusing. It might make sense if I change it slightly, and we'll still interpret the quantitative one here, but look at this. Two people who are otherwise identical. Otherwise identical would mean if we're going to compare someone to Brian, the other person, like there's Brian, and then there's a person who differs by Brian by 1 pound, but they're otherwise identical. So that person is also what? In this model right here, if I say otherwise identical, we'd say we have two people who are otherwise identical, but they differ by 1 pound. So we're comparing Brian to somebody who what? Think about the otherwise identical person to me in this model. They're also male. Does that make sense? So we're saying two people who are otherwise identical. We got Brian, he's a male. Now we're going to compare someone to him who differs by 1 pound, but they're also male. They're otherwise identical. So you can see this here visually also. When you look at this, look how there's two lines. We'll talk more about the categorical variable included in a moment, but notice how there's two lines. So if you want to compare two people who differ by 1 pound, you should compare who's to who's and who's to who's. Think about this. We want to compare two people who differ by 1 pound, and we want to talk about that difference we would expect between them, which is this little difference right here. If we're talking about that difference we expect, we have to compare these people to these people and these people to these people because they're otherwise identical on this other characteristic. So why do we say that? We're doing the why of it right now, which is so important. We compare males to males and females to females because, like, you're otherwise identical. Because if you compare a female to a female, well, two females that are otherwise identical, or two people who are female are expected to have this difference. Two males are expected to have this difference. So if they're otherwise identical, now you say, why don't you just say two males are expected to have this and two females are expected to have this? The problem is when you get into a really crazy multiple regression, well, here now, you're going to have tons and tons of coefficients. So rather than listing off all the coefficients to talk about the coefficient of weight now, we would say two people who are otherwise identical but differ in their weight by 1 pound. We expect the person who weighs more to be shorter by 0.02534. And I don't like not a big fan of showing scientific notation on the test, but that's 0.02534. Two people who are otherwise identical. Let me have you write it out. So there's the coefficient. I'm going to make it viewable. Remember, we're predicting height, and we're doing it with weight. There you go. We're predicting height, and we're doing it with weight. And this is a quantitative X. Quantitative. So that's why we don't list them all out. We don't say, but they're the same on this, they're the same on this, they're the same on this, they're the same on this. So what do we have? This is the practice for the test. And you've got your helper stuff right there. And you do get a cheat sheet for the test. So if you're practicing right now and you can do it with your cheat sheet now, you can do it on the test. So this is your practice. All the practice. Can you do it right now? Can you be like, two people are otherwise identical, but they differ in are expected, two individuals that differ in one weight by 1 unit, but are otherwise identical, are expected to average to differ. John, thank you so much, John. Good to see you here. Differ in height by point where the individual who is more. Yeah, exactly. Great job, Ella, right there. Excellent work, Ella. The only change I'd make is I'd probably say if it's just weight in pounds, probably throw that on, or like differ in their weight by 1 pound, because that'd be a 1. Like, I would not take out points. Just want to make that very clear. I usually grade the interpretations on these. I'd be like if you get to where I'm like, that's great. Two people that differ in weight by 1 pound who are otherwise identical are expected to differ in their height by negative 0.02533 inches. The higher the weight is expected to have a lower height. Exactly. Alyssa right there says two people who are otherwise identical but differ in weight by 1 pound are expected to differ in height by 0.0253 inches. Throw the inches on, just making sure we're doing A plus right here, Alyssa, 100 points. We're doing A plus, where the person with the higher weight is expected to have a lower higher weight is expected to have a lower height. Last part right there, where the person with the higher weight is expected to have a lower height, because the higher X expected to have a lower Y. Great work, Alyssa, right there. Excellent work. Two people that are identical but differ in their weight by 1 pound are expected to differ in their height by 0.025 inches, where the individual with the higher weight is expected to be shorter. Good job right there, Morgan. Great work. We're getting A+ interpretations. I would take off a small points if units is given. Context, context, context. Yep. It's maybe a half a point out of 4. I don't know. Look, we need a 320 grading meeting. Everyone gets the same grading. But those are some good interpretations. Make sure we love some A+. And everyone, I want to see some shout outs to Terry. I'm going to throw 200 points for every shout out to Terry we get right there. Terry, you're doing, I love working with Terry. Terry's our tool and coordinator, also teaches 320. And Terry is one of the nicest people I work with. I work with so many nice people, but I miss seeing Terry around the department. So give some shout outs. If you don't, as long as you say the less than, what if they don't give units? We should give context, right? Points for everyone. We will tell you the units. We will say like height is measured in inches, weight is measured in pounds. You could always do a little bit of an assumption if it's a little vague. And you can always dispute your test grades and say, hey, I think the grading was a little bit rough on that. And we can say maybe it was, maybe it wasn't. So always advocate for your grades. Advocate nicely. Say, hey, I just want to take a look at this, and I saw that I got 2 points taken off, and it was out of 4 points. Oh, we need some shouts for Terry right there. I'm gonna throw some 500 points in the chat. Okay, so let's do another one. Here we go with another version. But watch out. Shouts to Terry. Thank you, Joseph, right there. I'm gonna change something here because now, and we're gonna go a little simpler again. Well, not truly simple. But now I'd like to talk about this coefficient. I haven't put it in there yet. Thank you, Terry. What has changed about your world right now? What is different? So let's first identify what is different, because we have to know why we have to do something different right here. What's going on? And let me put the note in here as you think about it for a moment on what we're doing. We'll get to AIC. Thank you so much. There was an AIC question. We're going to do that here next. Interpretation is a big section. People might be figuring it out. Interpretation. And I'm putting one more note in here. We got a few more to do. Okay. It's a categorical quantitative variable. Great job, Alyssa and Morgan and Nicole. It's an indicator. That's what we call them. Female is the reference. Great job, Alex, right there. It's a lot of great information people putting in the chat. And so now we're on to indicator variables. Indicator variables. There we go. Categorical X's. How do you know what the reference level is here? How do I know... What's the reference level for that? How do I know that? And what is reference level? What does it mean to have a reference? Well, I always like using... Sure, I'll do it this way. I usually blank my screen. My stream deck's not working. First alphabetical. So if you think about the kids in my family, this is my example right here. Darren, Brian, Emily. Who, if I told my parents, who's your reference child? If I talked to my parents and I said, who's your reference child? Who would be the reference child in my family? It'd be Brian, because Brian's the first alphabetical. I mean, come on, it's Brian. So Brian actually really doesn't have an age. You could say Brian's age 0 if you'd like. Darren has an age of 3. Emily has an age of -2. Now, here's the thing. Brian is actually 40. How old is Darren? How old is Darren? This is what it means for something to be the reference. Brian is 40, and we'll just say Brian is 40. We'll put it here, Brian is 40. I am. Darren has a coefficient of 3, Emily's a coefficient of -2, and you're seeing it, you're getting it immediately. Gotta always remember to do it this way, and you don't see like negative. But it makes sense to say Darren's coefficient of 3 means he's 43, Emily's coefficient of -2 means she's 38. So when you think about this, everything is compared to Brian, So we call it the reference. My audio is not working. Oh my gosh. Okay. Everything's... Oh, we just need to reboot this. Update detected? Sure. Never restart your computer. Bad things happen. So now that we understand what a reference is, let's look at it here visually. So we're going to make this model right here. And we have a summary of it, but the visualization is really going to help us understand what the reference is. Okay, here it is. So when you look at this, can anyone tell me down to a few decimals how far apart these lines are? I'll throw out some 500 points. If you tell me down to 3 decimal place accurate the difference between those lines, and I'm talking about, I want some super exact how far apart these lines are. This difference right here, I want to know this. Like, you have to be really exact. You gotta be like, I don't know, maybe, let me try to estimate here. That's about 63. I don't know, like 5. What do you think? Oh, how did you know that? Oh, wait a minute. It's the coefficient. The coefficient right here is the difference. That's the difference. So think just class. And remember, what are we predicting right here? We're predicting height. And you can call it 5 in your interpretation. Don't trust. But let's just call it 5 for a second. So these two people right here, we've got Brian, and then we've got... So here's Brian. Brian's going to be up here on the Brian. And here is Elizabeth, which was my name if I was going to be born a girl. Parents picked up both names. Did they not, like, find out? I don't know. They were like, if he's a girl, I mean, they didn't know that. If this baby's a girl, we're naming it Elizabeth. That time they didn't know. So if Brian was Elizabeth, yet he was otherwise identical, what does this mean? Just don't interpret it yet, but just think about it. Brian weighs about 190-ish, something there these days. So, but just think about what it means. If Brian existed as Elizabeth right now and weighed 190, then what does this mean? Just think about, like, conceptually. What are we talking about here? We've got a person who is otherwise identical now. So we got Brian, got Elizabeth. They're otherwise identical. We expect them what? And this will lead to our interpretation. Well, males are generally taller. We do see that. We would expect males to be taller. Like, that's what we generally see. We would expect, and that's keyword right there. We expect, and general denotes that. Like, generally, we see males are taller, and there's a statistically significant difference right here between males and females. But exactly, right? Jesse said it perfectly right there. We'd expect you to be about 5 inches shorter. Does that make sense? So this right here is the expected difference between two people who are otherwise identical, i.e. they share the same weight, because you can literally go at any point and compare two individuals who are otherwise identical, but one is male and one is female. Now notice there we compare the indicator to the reference. Sometimes there's more than one indicator. So how do we interpret this? Take a moment, we're going to put on that music. Who's got our interpretation? Let's grade those interpretations. We're interpreting the coefficient of gender, and I'm going to give you how to do it over here while you think about it. So 2 blanks. Remember, you get a cheat sheet. Let me zoom in on this a little bit here. Who's got this? Who has our interpretation? The coefficient is 5. See if it makes sense as you say this. 2 individuals that are otherwise identical, but one is male and the other is female. The one that is male is expected to be... Yeah, there you go right there. 2 individuals that are otherwise identical, one is male and one is female, one is male. The individual that is male is expected to be 5 inches taller. Great job. Is it making more sense? Like, I know we've done these interpretations a lot, but is it starting to make more sense? Like, especially when you see it visually and you're like, oh yeah, two people who are otherwise identical, but one is male and one is female. The person who is male is expected to be about 5 inches taller than the person who is female. And I say about because it's 5.025, yada. But is it making more sense, like, as you see it and be like, yeah, that's the expected difference between two people who are otherwise identical, or one is male and one is female. We generally expect to see about this difference between them. And that's the predicted expected difference between them. And it's just mathematical right there. That's what we want to start seeing and why we interpret it this way. And you have to watch out. You don't want to say things like males are this much taller than female. And it assumes the same exactly, because that's the other. So wait, Alex, 100 points online right here. Everyone's like 100. Brian, you give it 1,000 all the time now. Got to stop the point inflation. The key phrase that assumes the same weight is what? The key phrase that assumes the same weight is the very important and multiple regression phrase of this. The key phrase that assumes same weight, because we want to compare things that are what? The key phrase that assumes same weight in the writing of the interpretation is what? What's that key phrase? Otherwise identical. So we got two people. They're otherwise identical, but one is male and one is female. The expected difference between them is 5.025 inches. Great job, Mary, right there. Excellent work. And Nicole and Morgan and Alyssa. So two people who are otherwise identical, but one is male and one is female. The expected difference in their heights is 5.025 inches, where the male is expected to be taller. And just try doing interpretations like this. Try writing it out. Remember, you're always predicting the Y variable of interest. The more you do it, the more comfortable you get with it, and the more you can explain it. And then if you went to somebody who you weren't going to stats see, you could say, well, generally, everything else the same between people, like they're the same weight. We'd expect males to be about 5 inches taller. Be careful. The more you go outside, the reason some people say, well, do I have to say it the way we say it? I'm like, well, there's ways to improvise on it. But the more you improvise, you could go into that territory where it gets into a little like, that doesn't really work. So I try to make a structure that everyone can do it with to keep people towards what always works for interpretations. But if I was in a boardroom, I'd say, generally people who are the same weight, but if one is male and one is female, I'd expect the male to be about 5 inches taller is what we predict for our model. That's what I would say if I was in a boardroom. I wouldn't do the 0.025. I would just say about 5 inches, because that's about 5. I mean, the measure of uncertainty is pretty large on it for, like 5s within that. Okay, so now we have to switch our gears. We've done quantitative. We've done quantitative categorical. And here's where people usually lose a lot of points on the test, is because most people forget that the last month or so of the class has been focused on this type of model. Let's put the model everyone forgets. And I'll start doing it right here. Who can tell me what model? I was doing it right. What model does everyone forget right here? What model is often forgotten? The forgotten model that everyone's like, oh, wait, it is different. Logistic. So logistic, let me take a note right here. Logistic regression is where people say, wait, is this different? I say, yes, it is. So logistic regression, quantitative or categorical with a quantitative categorical Y. Let's try. I'm taking the note right here. Logistic regression with quantitative X. Okay. So what makes logistic regression, great job, Makai, right there. What makes logistic, can you explain to me what is a logistic regression? Why do we use it? What is logistic? Why do we use it? What the heck is this whole logistic thing? It sounds super complicated, but then when you're like, oh, we're just doing this. Categorical Y, exactly. So the Y of interest right here is a 2-level. There's actually a thing you can do called multinomial logistic, which is a multi-level Y. We do binomial. Great job, KP, right there. We're predicting a categorical Y, and the common logistic, known as just general logistic regression, is a 2-level categorical. If you do a multi-level, it's called multinomial. We're not doing that. We use it for yes, no, right there, Makai, that's correct. And that's what, for most purposes, if someone says they're doing logistic, unless they're going to multinomial. Enough on that. Multinomial's not on the test. So now when you look at your model, it'll have a what shape to it. The logistic curve has a what shape to it. The logistic curve has a what shape to it. You can name the letter. or name the fun sigmoidal, which means it's an S shape. So now we have a sigmoidal S-shaped curve. And I just want you to think how this model works. We are predicting the what of somebody being male. We are predicting logistic models predict the what of Y. Logistic models predict the what of Y. Logistic models predict the what of Y. I guess logit if you want to, but we don't use logit. Logit is then turned into probability, and we'll look at that equation here in a little bit. We're predicting the probability, and now you have to be careful. It's on the screen. Oh no, it's even bigger now. We've got female and we've got male. We've got a saying in our class. What is the saying? Got a saying in our class to help us remember what the level of interest is. So try to remember, this is not on the test, but it's a good way to remember. Oh, in this, the this is this. Because it's reversed for reference levels. Reference levels are the first alphabetical in, what is it? Who knows this phrase? In logistic, the level of interest is last. So we're kind of highlighting the L's in there. Take those L's right there. In logistic, the level of interest is last. Great job right there, Ryan. Does that make sense? In logistic, the level of interest is last. So think about this. Female, male, level of interest is male. When we say interest, that means all the probabilities are going to be associated with male. Does that make sense? So could we figure out probability of female? Like, let's say we take Brian over here. And just hypothetically right now, we run the model. Can anyone just guess Brian's probability of being male? We'll figure it out here a little bit later. But we run the model. And who's got a guesstimate of Brian's probability of male? What is Brian's probability of male? There you go. Makai's already done it right there on how to figure out the probability of female. Because with Brian's probability of male, let's just guesstimate it. We're just guesstimating is something like 0.9, let's make it easy on ourselves, 8, 94%. I'll go with that right there. So what would be Brian's probability of being not male, which this model's binomial? So, or Alyssa might actually, Alyssa, if that's the right answer, I'm throwing like 1,000 points. Alyssa might already have solved it. That's something around there. I think it's probably closer. Alyssa's answer might be closer. It's probably a little more than my guess. We'll find this out here in a moment after we interpret the coefficient. That's my guess. I think I've ran this before. That's my guess. We'll find out here in a moment. But it felt like the right answer. That's a good guess, Alyssa, right there. So we could take and then Makai, make sure 94%, it'd be 6% the other one. Oh, has Terry already solved it? Dun, dun, dun. Terry's got the right answer. We're throwing 1,000 points for Terry. I think Terry might have the right answer. I think Terry's got it. We'll find that out here in a moment, but let's think about how we would interpret this. Now, life gets a little bit easier here. Remember, we're focusing on interpretations, and we're doing some practice problems on these. So with the interpretation, let's look at the coefficient. Now, there's something we need to know for logistic. I want you to think what happens if I interpret it this way. This is a bad interpretation. You ready? This is a bad one. Don't write this down. Pens down. Okay. Don't write this down. Two people who differ in their height by 1 inch differ in their probability, are expected to differ in their probability by 7% of being male, where the person who is taller is more likely to be male. What do you notice if we expect people to differ by 7 inches? The 7 inches, or 7% probability. Correct, Nicole, right there. Nicole already knows what's going on with this. What would happen if we kept increasing the probability by 7%, which that's not meant to be interpreted as 7%. It's different in logits, which we don't do logits. You don't use the coefficient. You just use the sign of it. So if you kept increasing by 7%, then what you would see is you would leave the 0-1 boundary. Does that make sense? A difference of 7% over a large interval is going to leave the boundary of 0-1. So you can't talk about people having an expected difference in percent of this amount. The only thing, repeat it with me. I need a few more people to repeat this. Nicole and Nakaya both see it, and this is a huge error. Put this on your cheat sheet. In logistic, only interpret the what? In logistic, I'm going to put it on my cheat sheet over here. In logistic, only interpret the what? In logistic, only interpret the what? The only thing we focus on in the interpretation is the what of the coefficient. Oh, boop. You gotta grind. Stop distracting me. Only interpret the sign. Great job, Mary and Makai right there. Only interpret the sign. The sign is the only thing you should focus on. The sign. And just think if this makes sense in your world. I want someone to say the interpretation and be like, well, no, duh, come on. I want you to interpret the coefficient right here by noticing the sign is positive and then looking at the graph. So think about this. I saw some ace of base. I saw the sign. Interpret this coefficient right here and then see if it makes sense to you. Now, remember, we're not in a multiple world. So let me put the blank interpretation right here. Two individuals that differ in X by 1 unit. The individual okay. Who's got it? Let's see. There's a blank interpretation. Now be careful. We're not in the multiple world. I probably wouldn't take off points. We're not in the multiple world right now. What do I mean we're not in the multiple? There's just one X. That's how we know we're not in the multiple. This is called the simple world. It's very simple. There's one X. Simple world is one X. Multiple is multiple. But what do we have right here? Let me try to get it so you can see everything at one time. Remember, I can't disappear right now. Those buttons are not working for some reason. So what do we have right here? This is a quantitative X in a logistic. Quantitative X in a logistic. How do you... Two individuals that differ in height by 1 inch. The individual with the higher height is more likely to be male. Oh, you have way more right there. Ella, right there, you're using the quantitative from the last one, is more likely to be male. So two individuals that differ in height by 1 inch. The individual with the higher height is more likely to be male. Does that make sense? Two individuals differ in height by 1 inch. The person with the higher height is more likely... by 1 inch. Oh, yeah, no worries. Comparing two otherwise. And then we don't need... I would probably not take off points, Alex, for that. But there you go. Comparing two otherwise identical, let me read. Comparing two otherwise identical, one who is taller is more likely to be male. I'd be a little iffy on that, Alex. I'd make sure a few things. Make sure, like, you could say things like, if we look at two individuals, where one is taller than the other, the person who's taller, I'd predict is more likely to be male. Make sure you don't say you predict they are male. That came up in our class. Because think about these two people down here on the graphic. If you had two people down here, because we were talking in our class when we first did this, someone said, well, isn't the person who is taller, they are going to be male? Need to be a little bit smaller. We can't say they're going to be male because what if we talk about two people who differ in height by 1 inch, but the first person is 65 inches and the other person is 64 inches? Then we would predict both these people to be what? Both of those people would be predicted. Oh, Charles, good to see you here. Anytime, Charles. Great to see you. Both of those people would be predicted to be not male. Does that make sense? So, but the person who's 65 is more likely to be male. So you'd say, well, these two people differ in height by 1 inch. The person who is taller is more likely to be male. So that makes sense. We're not saying they are male. We're just saying it's more probable according to the model and the way the mathematics works out. So we get into some problems right here because we need to know how to solve for the probability. Now, I will say this. These are some of the questions where I only see around 30-40% of people get it. Who just perked up right there and said, wait a minute, only 34% or 30 or 40% of people are going to get this? That means see if you can solve it. If you can solve it, you're on the right track. Predict Brian is 75 inches tall. Predict the probability of Brian being male. Predict Brian's probability. On one screen. Remember, solve it yourself. If you see me solve it, that's one thing. But take a moment here and solve it. I'm going to show you how to solve it in a moment. We've interpreted the coefficient. We can see the model. Any numbers you get should be contained between 0 and 1. That's a hint. If you get outside of 0, 1, you did something wrong. So see if you can solve it. We'll look at what answers we get. So this time, actually solve it. Like this time, run it through the equation, carry all the decimals. If you have R open, put in all the decimals, solve it out. And so let's see how to solve it. I'll show you my best way of solving it, the way to consistently solve it and get the right answer. But you're making a prediction with a logistic model. So so take a moment here, solve it out. I'm going to show you how to solve it. Don't worry if you get it wrong. This is the practice. This is the time to get it wrong, to get it right. Let's see what people are saying. We'll wait for a few answers to come in. Did Terry get the right answer? Terry said 99.4. Did Terry run the model? So I think I know what you have right there, KP. So think about what you just told me. And so KP, we're throwing you 1,000 points. Something, I think I could use that to solve the right answer. And I think I know what you did. Where am I typing the points in? So this is great for you, KP. 1,000 points. You're going to see the error you made. So take a huge note right here. Be like, oh, I got to remember to do this. Because you're one step away from getting the answer now. We'll see if anyone else has some answers here. But I think I know what you did. You'd be like, well, don't we just do this? I say, yes, but there's an additional step with logistic. We'll see if anyone else gets this. Once again, these are the things that people just don't remember. It's all right. Like, I've taught this class for like half a decade. Haha, it's been a while. And this is where people make mistakes. We'll see. Anyone else? 0.8226. Well, that's what... that is correct. So let's take a look. No one got it, which is good. That means we're doing things we need to do. Ella, that doesn't sound quite right. Because when we estimate this, remember we estimated it earlier? So looking at it visually... Alexander. I think Alexander may have it. So, and then Chase got it right there. So remember we looked where Brian was at on this curve. Brian's over here, right here. Sorry. I cannot. There it is. Okay. I can't disappear, remember. My thing's broken. Okay, so I can't go boop, or I'll have to go to the screen to bring myself back. So we know the answer we get has to be contained between what and what. Remind yourself on logistic. Oh, no worries, Ella. On logistic, any answer you get has to be contained between what and what. On logistic, this is a good reminder, any answer you get has to be contained between 0 and 1 because you're predicting probabilities. So make sure whatever answer you get is contained between 0 and 1. And we'll see another example here in a moment. So KP, you did the right thing. So check this out. You're like, well, then how did I get it wrong? We're on that in a moment. We're going to take, and let's just call it y, and we're going to take the equation. We're just doing intercept plus coefficient times x, and we'll put in here height. And so now we need to put in a height value, and we'll put in height 75 inches. And, oh, haha, I still forget that even to this day. And so that's the answer, right? That is the logit. We don't use the logit. We then have to take this and plug it into any answer in logistic is plugged into the following. It's plugged into e raised to the value over 1 plus e raised to the value. And the reason is because this creates the sigmoidal curve. This is the equation of the sigmoidal curve that locks it in. Because as we have e raised to infinity, it goes towards 1 because it goes towards infinity over infinity plus 1, which is 1. As it goes to negative infinity, it goes to 0. I go into more detail on that in the lecture, but trust me, or you can watch the lecture on more detail where I explain how this creates a boundary that the curve is locked into, and it's going to create this sigmoidal shape on it. So now by taking this number that we obtained right here, it's literally going to be plugged into this curve right here. We'll put it back to y's here in a second, and we achieve the following probability. Does this make sense? And if you'd like, is anyone closer to 5 feet tall? As long as you're willing to say your height. Let's just think about your prediction for a moment and how it works out. If you want to say, and so go ahead and say, as long as you're okay with saying it, be like, I am this many inches tall. Or like you can just put the inches. And we'll use that right here and think about what we should get and how this works. 5'2" right there, so 62. Thank you so much, Mary. Let's make Mary a mod right here. Mary, one of our not mods. And now you are a mod. Thank you, Mary, right there. 62. So what's interesting is if we plug in Mary's height right here, and thank you, Mary, we actually get y is going to be what? Think about this. The value of y currently, because remember, Mary, 62 inches right here. When we get the logit, the logit is actually going to be a what value right now. So the logit, which is not the final solve, the logit is actually going to be a what value, which we're then going to plug it into the e raised to over the 1 plus e raised to the. So the logit is actually going to be a what value? The logit is actually going to be negative. Exactly. The logit's going to be negative. Take a look right here as we solve for it, and we see that y has a value that is negative. And actually, Mary, I think your probability is going to be about 1% of 1%, because look, I'm over here, Mary's over here, and when we solve for it, it's probably going to be about 1%. There it is right there. That's 1,000 points right there, because that was somehow I didn't even plan for this, but that's the perfect example where Mary's value and my values are almost perfectly away from each other, in the sense that over here at 62 inches, you have a 1% probability. Over here at 75% or 75 inches, you have a 99% probability. So think about this. Let's think about this just a little bit right here. 62 inches to 75 inches. Where about would somebody have a 50-50 probability of being male? Where about would somebody have a 50-50 probability of being male? Where about? I'm trying to solve it in my head too right now as we do this. Where about? Because Mary's over here at a 1% probability. Oh, Chase has already solved it out mathematically for us. Around 68 inches, and Chase has taken and solved it out. Chase, that's worth 100 points. Chase is correct that if we take the ratio of these, if you take the negative, Chase has typed it there. He'll show the 50-50 change point. Like when someone has a 50% of either level, change point can be found by negative B0 over B1. So let's take that. We take the negative intercept over the slope, and we're saying about 68.5 inches. And check it out. That's what you were estimating. Does that make sense? 68.5, and you figured that out. And what happens when we plug this in? The logit is now equal to what? Think Mary had a negative value. Brian had a positive value. If we plug this in here, the logit is actually going to be equal to what? Or very close to. We might not have calculated enough decimals. But remember, Mary was negative. She had a probability below 50%. Brian was positive. He had a probability above 50%. So think between those numbers. Basically 0. And we just didn't carry enough decimals. But the way the equation solves is if you plug in e to the 0 over 1 plus e to the 0, e to the 0 is 1. So the mathematics here work out. And that's why we do the ratio of the two to figure out like where they would kind of cancel each other out, and you would get the e to the 0. So kind of some neat stuff right there on how it does probabilities. And one of the big things we've been focusing here on is the interpretation that two individuals who differ in their height by 1 inch, the individual who's taller is more likely to be male. Now, if we go to the multiple world, so let's do the multiple, and we just add in here weight, it's still simple. Not simple world anymore. But how would we interpret the coefficient of height right here? So now we're in the multiple world. This is now multiple logistic regression. It's logistic because we have a categorical Y. So how do we interpret the multiple logistic regression right here? How do we interpret the multiple logistic? What would we say? Remember, we're in multiple logistic. Well, we'd say more likely. So what would you write on the test? What would be your test answer to this? What would be your test answer? How can you plug in EXP into calculator if R is not available on the exam? On your calculator should be, well, E is 2.7182818, 284597818. You can do that right there. And then do raised to 0 when you solve for that. Then you can get the 1 plus this right here. And you could plug in like Brian's value, which was like 4.5 if you needed, and 4.5. So write down 2.718 if you want, and then you would divide these numbers right here. And there's Brian's probability. And then carry decimals and stuff. E to the exactly. You can do e to the x. Like most calculators should have e. And does that make sense right there, Morgan? Good questions. E being 2.71828. 1828 is nice and fun. It repeats a little bit. 1828, 1828. Anyway, fun. Good stuff. And so, yeah, good job, Morgan, right there. Thank you, Morgan. 100 points. Good questions. Let's prep for the exam. How are we going to interpret this coefficient in the multiple regression? So now, I think, was it Alex and people for below 0.05, we say we predict they aren't correct. For, was it Mary? You would predict that Mary is not male. And for Brian, you'd predict he is male, or you might not know. So you'd say, I predict Brian's male. I predict Mary is not male. Usually I just like to say not the level of interest. So Brian with the 99% probability, because it's above 0.5, to Ella right there, 0.5, it can get interesting with alphas and stuff. 0.05 is the assumed alpha. 0.5 is the point at which we predict the level of interest. And if it's directly at 0.5, a lot of algorithms will actually flip a coin. Like a lot of algorithms that use logistic or models that make predictions on probabilities will actually randomly assign if it's 0.5 on the dot. We won't have you solve one that's 0.5 on the dot. So, oh, I think my mom cracked up. I said that in front of her. She was like, "Dot," and I was like, apparently the things you say in class all the times as jokes start to go into your language. So I make too many jokes and it becomes reality. I become the joke. Who has our interpretation of this coefficient? This is practice for the test. Who has the interpretation of this coefficient? Remember, this is a logistic where we're predicting the probability of somebody being male. You can see the model that created it right here. There's the model that created it. There's the coefficients and model. Which of the two can you explain? Can you expand upon that, Ella? Which of the two is better or right? We won't give you one that's exactly 0.5 on the test. Like I would say, no. Algorithms will do it for you and flip coins in the background. Like they do a random number generation to do the prediction at 0.5, because we shouldn't assign the 0.5 all to like the level of interest group. So that's a little bit of like how advanced algorithms do it. They don't do, I think we are told a lot of times in literature, if something's 0.5 to predict it, but people who wrote the algorithms know a little bit. They're like, no, you wouldn't do that. Yeah. Like say it's not the level, whichever you prefer. This, like we would count either one to when somebody like for predicting for Mary, the way I always say it, and great job, Makai, right there, we'll read that in a second. The way I always say it when I'm predicting not the level of interest, I would say is someone is predicted to not be male. Does that make sense? You could, that the other level here is female. Like we are predicting a binomial in this model. So you could say they are predicted to be female. I prefer to say they're predicted to not be the level of interest. So I always interpret it that way to say Brian is predicted to be male, Mary is predicted to not be male. So I like to do it that way. You're always not the level of interest is your prediction if you're below the 50% mark. Now we might know what that level is and then say it right there, which either one's fine. Yeah, it's just maybe your boss wants to interpret it a certain way. So you say, hey, do it this way. Two otherwise identical individuals that differ in their height by 1 unit. The individual with the higher height is more likely to be male. Makai, great job right there. So if you notice, everything here was the same. And we've just done the same thing right there. So that's the answer. But now we get into where it gets a little bit more complicated. Because now we've done a categorical Y with a quantitative Y with a quantitative X. Now we need to go over here. It's going to get weird. And we need to do the following. And I'm going to do a hint for the take home. What is interesting about this model right here? And let me ask you before I run it. You can be left-handed, you can be right-handed, or you can be ambidextrous. How many indicators will be in this model? You can be left-handed, right-handed, or ambidextrous. How many indicators are in this model? You can be left-handed, right-handed, or ambidextrous. I think people are saying the chat. Categorical. Oh my gosh, 2 seconds. Categorical. There we go. You can be exactly 2. Once you've added weight to the model, that's when you add the otherwise identical to the... correct, when there's multiple X's. So when you just have 1 in the model, you can just say 2 people who differ in their height. But as soon as you add in the more X's, then you're saying otherwise identical. Audrey, great question right there. As soon as you add in multiples and people are giving the correct answer, there are going to be 2 indicators. What is going to be the reference level? Who has me on the reference level before we see it? Remember, we have right, left, ambidextrous. So the reference level is definitely, and you can put 1 letter in the chat, I'll know what you're talking about because I can't spell it either. That gives you a hint right there. But the reference level that everything will be compared to is what? The reference level that everything will be compared to is what? I actually want to see this model, so I'm going to do it this way. The reference level that all of them will be compared to is the what level? A, ambidextrous, right? So A, there it is. I don't see it. Wait, is something wrong? I don't see ambidextrous. I just see left and right. Yeah, we might be. Yeah, Haley, we'll try that. We'll put that on the list. You bet, Haley. We'll go over. I think we can. We did some during class. We'll do. You got it, Haley. Let me put it on the list. 11 model hierarchy. Why don't I see ambidextrous? Well, it's not the level of interest. Ambidextrous does not have a coefficient. It does not exist in the output. We don't see level of interest in. Excuse me. We don't see reference level in output. We don't see the reference level in output. Does that make sense? Level of interest goes to the Y in a logistic. Reference levels are all about the X's. You don't see the reference level in the output. You don't see it. There are ambidextrous people, and we can confirm this by going over here and just visualizing the model. So if we visualize the model, we will see there are ambidextrous people. They do exist. So you have the ambidextrous people here, and I want you to just look at this. Looking at this here visually, who is more likely to be male? Just look at it visually. We'll worry about the coefficients here in a second. You've got here the ambidextrous, which is our reference level. Who is most likely? It won't be statistically significant, but who is most likely to be male? Left-handed people, right? Because if you take 2 people who are otherwise identical, they have the same height. The person who is left-handed is most likely to be male. Does that make sense? And the person who is least likely is ambidextrous. What do you now know about these 2 coefficients? You have actually just figured something out about these 2 coefficients because you're saying they're more likely to be male. You've just figured something out mathematically about those 2 coefficients by looking at this output. Because you're saying, well, if I compare 2 people where one is ambidextrous and one is left-handed, the person who's left-handed is more likely to be male. If I compare 2 people where one is ambidextrous and one is right-handed, the person who's right-handed is more likely to be male. They're otherwise identical. You know what about these 2 coefficients now? Because they're more likely. That's the key thing that we just figured out. They're more likely. So we've just figured out the what of these coefficients. Since they're more likely, we know that both of these coefficients must be what? Because remember, they're more likely, which goes to the interpretation. We now know both these coefficients are positive, exactly, because they're more likely. So remember, we're going to compare them to the reference, and we just figured out the sign of both of these coefficients. They increase the probability, which when you look at the output right here, take a look, both coefficients are positive. And by positive, I mean this portion right here. So 2 individuals who are otherwise identical, where one is right-handed and one is ambidextrous, the person who is ambidextrous is less likely to be male. Whoops! The person who is right-handed is more likely to be male. We usually interpret in terms of the indicator. Right-handedness is the indicator. And a good way to know that these are indicators is whenever you have an indicator variable, you always see the variable name, and then you see the level indicating inside of it. The variable name is what right now? Just confirm you see it. I know I've got it highlighted, but the variable we are using is called what? Like the name of the variable. The name of the variable is called what? And then we can see the indicator level. The name of the variable we're talking about is handedness. But then there is a level inside of it that creates an indicator variable. So the indicator variable is handedness right. Now we have to compare that to something. This coefficient only makes sense if we say compared to people who are ambidextrous. And you can see the least likely people to be male are ambidextrous people. Now, someone might ask you, is this statistically significant? And once again, hints for the take home. how could we figure out the overall impact of this variable right here? Like, is handedness significant in this model? Is handedness significant in this model? How can we figure out the overall impact? Drop one right there, KP, great answers. Hint on the screen. So what you have right here is the drop one. You have to do test equals chi-square. No. And take a look. What also does, maybe, you know, if you make models, I'm just saying, what maybe do you want to do with any model you make if you can? Because we need to get in the practice of doing these things, even if we're not asked for it. What should you maybe do with models to help give you an understanding, a good first step to understand and see what's going on with your models, which sometimes gives you additional information, like when you run it, oh, look at that, an effects test, which is the drop one, which did the same algorithmic work for me of doing this right here, visualizing it. They are the same, exactly. Micaiah, great work right there. An effects test is a drop one where we remove one variable out. It works the same if there's interactions, like if we had an interaction right here. Hint, hint, hints. What? Oh, that's fine. I don't care. And if you do that right here, whoa, oh, you can't see it. It's due to the lack of data. It creates that crazy. But the interaction is done right here. And so you wouldn't be able to tell the p-value of the interaction unless you did the drop one, or you did the drop one. Oh, I don't have it listed. Drop one, m test equals chi-square. There you go. And look at that. Same p-value. So I highly suggest visualizing all your models. That's a big hint right there. Visualize your models. Take a look at what the output you get. It's going to lead you along the right path to say, like, oh, that's the interaction between the two variables. I think that does it for all of our interpretations. I think we've covered them all. This would be two individuals. Did we miss anything? I don't think we did. We're on to AIC now. So let's put a break in the video right here. But let me ask before we move on, what questions do you have? Do you need any help? Do you want to do another interpretation on something? But this whole segment right here has been on, can you reiterate drop one, like exactly what it does? So what it does, drop one does not break model hierarchy. More on that in a moment. It removes one variable at a time. It's rather boring if you don't have fun variables in your model. So drop one drops one variable from your model and compares it to a model without that one variable. So if you do this right here, drop one's going to be super boring. Because the drop one right here is just doing what? Like, just think about what drop one says it's doing for you. It's dropping one variable time. Can you go over the formula for logistic? Yeah, we'll do a whole segment on that, Alex. Good question. We'll do some predictions and do multiple questions. This is boring. Yep, we'll do some model hierarchy coming up here soon. Does everyone understand why this is boring? Let me explain why this is boring. Because we already get the p-values for these where. These p-values are already where for us. Or estimated, it's going to be similar in the way they're estimated. Because these are just one thing being dropped. We already have the p-values for these in the what? We already have the p-values for these where? In the summary. We already have the p-values for these in the summary. But what about if I add in here handedness? Why don't I have the p-value for handedness in the summary? Why don't I have the p-value for handedness in the summary? I mean, I have p-values, but why are those not the p-values for handedness? These are the p-values for the difference between left to ambidextrous. This is the p-value from right to ambidextrous. This is not the overall impact of handedness. So when this is considered one variable, and that's what the one of drop one stands for, is dropping one variable at a time. So this is going to do a partial F where we say, let's remove handedness. Now, if I remove handedness, how many things am I taking out of the model by removing handedness? I know I'm taking out one thing, but how many coefficient estimates am I removing from the model? So when I remove handedness, I'll be removing this many coefficient estimates to compare a model with handedness and a model without handedness. Careful, there are 3 levels, but I'm removing how many coefficient estimates? How many coefficient estimates am I removing? 2 coefficient estimates, because the 2 are created to compare. So we're removing 2 coefficient estimates. Hence, in the drop one output, what do you notice right here? Degrees of freedom are the change between the coefficient estimate differences in the model. And you'll notice right here that we have a difference of 2 degrees of freedom. So this right here, this p-value is the p-value of a model that has handedness compared to a model that does not have handedness, telling us that the overall significance of handedness is what? Which that's the answer over there. The overall significance of handedness is what? Hence high p-value, telling us if it brings with it new information to the model. The overall significance of handedness is what? Not significant. So what would be what does this mean? What does this have us conclude when it comes to our model? When it comes to our model, it's like, maybe you know what are we thinking? What does this tell us? Why does a stats person need to look at that? What have we concluded from this? What have we concluded? Whether or not it's useful. Like, should we be using this? Is there reason to include it in the model? And it's like, maybe we could throw that out. Probably not a good predictor of gender, exactly. So maybe that's really not helping out. And we wouldn't look at these p-values because these p-values are the significant difference from the reference level. That's how they are compared. This is the estimate of the difference from the reference level. Yeah, no, good stuff. Great questions. And we've only got 2 more things on here. We got AIC and model hierarchy. So feel free. Oh, and then we need to do predicting with logistic. Thank you so much. We got AIC predicting with logistic. AIC and what it means in predicting with logistic. What is the exact interpretation that we would write for the cat X and the cat X and the Y? Again, which one? Do you want a cat X and a quant Y, or which one do you want to do? Or we do all of them. So here we go. Here's the interpretation of the height coefficient. First thing you should look at here is what, Ella? The first thing we need to know, cat X, cat Y. Okay, cool. We'll do that one next here. We always look at the what when doing logistic. Only care about the what. I'm going to do this one here first and take a look. We only want to look at the what right now when doing logistic. We're predicting probability of someone male right now. Only look at the what. First thing we said, only look at the sign. I saw the sign right there and I interpreted the logistic right. We should do that. I saw the sign and I interpreted the logistic right. I'll never sing it again. Okay. So we have here 2 individuals who are otherwise identical, multiple regression, who differ in their height by 1 inch. The person who is taller is more likely to be male. That's it. Now we go over here to a categorical. Gotta go. Great job, Micaiah. See you later. We go over here to a categorical. So let me, Ella, take a shot at it. See what you get. Try to interpret it. Remember, you're just combining together. Look at the sign and think about what the reference level is. Give it a shot, see what you get, see if you can do it. Great job, Parker. What do we have? Who has an interpretation? My mom is sending me photos. Looks like a meme. Who has an interpretation? Give it a shot, see if you can ace it. It's going to be very similar to what I said, but you need to do a reference indicator combo. So a reference indicator combo. Time to practice. If you're sitting at home right now watching this, write it down or try typing it out. We'll see what people say and we'll see how close they get. Put it on your cheat sheet. Let's see. Remember, we're predicting 2 individuals that are close. Close. We're missing a key component. Anytime you talk about indicators, you must mention the what. Alex and Ella, great job right there. That's why we practice. Terry's right. We're here to practice. We're missing in both interpretations of what right now. We're missing in both interpretations of what. You need to compare them to someone. They're more likely. More likely than who? So anytime we do an indicator, we have to have a reference level. So what are we missing? Pretty close. On the right path, we notice the coefficient is positive. I mean, it's with the highest coefficient, one of the highest ones, right? 2 individuals who are otherwise identical. Yeah, it's here right there. Right? Morgan says, but they differ in handedness from ambidextrous or left. The individual who is left-handed is more likely to be male. Boom, Morgan right there. Great job. And there we go. They're more likely than ambidextrous. And Morgan right there, that would get all the points right there when I'm grading it. 2 individuals who are otherwise identical, and I would probably say, but one is ambidextrous and one is left-handed. The person who's left-handed is more likely to be male. So great job right there. You could say they differ in their handedness. Like if you want to, because that's how we talk about like they differ in their X. They differ where one is ambidextrous and the other is left-handed. So great job right there, Morgan. Good practice. And just think about what you're saying with it and what it means visually. I do have a different visualization currently up. This is the visualization right here you're talking about, where you have an ambidextrous person and you have a left-handed person, and you're saying two people where one is ambidextrous and one is left-handed who are otherwise identical. They're the same height. The person who is left-handed is more likely to be male. Alexander, another 100 points. Great work right there. And just look at it while you're saying it. Two people who are otherwise identical, but one is ambidextrous and one is left-handed. The person who's left-handed is more likely to be male. There. Exactly, because ambidextrous is the reference. Alex, we're just going crazy on points to Alex. You're doing excellent. Great practice here. Keep it up. That's what we want to see. Just keep typing it out. Keep seeing these things. The more we say it, we repeat, and put it on your cheat sheet to prepare for the test. I will say this, working together with people on the cheat sheet you can use, not an actual cheat sheet, but working with people on your sheet for the test is good. But the more you're writing it down, the more you learn from it. Have you ever gotten a study sheet from someone that you can use where you're just like, I don't even know what's written on here? Or have you ever written your own study sheet and been like, oh, I don't even use it because I learned it by writing it down so many times. I'm like, oh, I didn't even look at my study sheet because I looked at it so many times before the test. I'm like, yeah, I know that. I don't even look at it. So it helps a lot. No, sorry, Alex, they don't carry over. I wish they did. Your hours carry over, not your points though. So you get to have the thing of hours. And then I do give people meme stats as they want. You can't have simple logistics without a correct. So simple logistic only indicates categorical, not cat X, but cat Y, Alexander. Does that make sense? Logistic is defined by the what variable in the equation. Logistic is defined by the what variable in the equation, which means we're doing probabilities. Logistic is defined by the what variable. Just the idea of logistic is defined by what. If you say logistic, it means your this is this. Then we're going to do ASC next. If you have logistic, it means your Y is categorical. Oh, no. And you can have both. You could literally just do this model right here, which is a categorical Y and a categorical X. And so there's the model right there. It's going to, I don't even know. I don't know if we can visualize this, but it does work. It is math. Might not visualize. It's mad, but the math works out. It just might, I don't even know how that, how is that even going to look? It's only making three prediction points. It would predict three separate probabilities. So that's really good. Can you show how to do the prediction formula again? Yeah, Alex, here let's do that right here because it's a good moment to do it. We'll do AIC next. We'll do a whole predicting with logistic right here, and we'll start off. This is a good jumping off point. Thank you, Alex, for asking that. I think it's a good jumping off point. We're gonna do AIC next, but this is a good point to do the predicting with logistic you asked about. Okay, predicting Y with logistic. Okay. Take a moment right here. This is a ridiculous logistic model, but it can exist mathematically. I want you to predict your probability of being male right here. And then funny enough, I might be able to tell you your handedness. I probably can. Who can predict, take a moment and predict your probability. And that's a good way, logistic, of being male. Okay. Predict your probability in this moment. As long as you feel okay with putting the probability out there and also stating your handedness, predict your probability. And I'll tell you something pretty quickly about you, probably. Okay. Not a very good model right here, but let's use it. So let's write out our equation first, the overall equation. Try solving this as I'm doing it. The overall equation is prob male, or logit prob. Because we're not going to solve for it yet. We're going to solve for the logit first. Let's see. Has anyone got it? No one's got it yet. We need the intercept. Copy paste. Intercept. We're going to abbreviate these. Oh, well, two people where one is right hand, one is ambidextrous. The person who's right hand is less. That is correct. And so do your probability, though. Predict your probability. So now we're doing probability predictions. So try predicting for yourself. As long as you're okay with putting your handedness out there and putting your probability out there that the model predicts. Try to see if you can do that right here. So you are going to put your value into this equation. This goes to a lot of important topics right here. Oh no, Alex, you're doing fine. Alexander, excuse me. You're doing fine, Alexander. So just take a moment, see if you can solve it, and then I'll show how to solve it. If you're rewatching, a great time to practice. We always give everyone a moment to solve this and we'll see what we get. Nothing wrong with getting it wrong. It means we need to practice. We get it wrong in class to get it right on the test. Mine is 0.4421. I have a feeling you are right-handed, Alyssa. Are you right-handed? And you say, well, how did Brian know that? How would Brian know that I am right-handed? Wait a minute. Ooh, I might have a hard time. I think this model actually predicts no one's male. Darn it. I need some more. That is correct. Chase, ooh, Chase, I think something went wrong in your predictions. We'll find out here, Chase, 100 points. Something, but we'll check this out. Let's check this out. Are you ready? I think it predicts no one's male, actually, as I look at this. I think everyone's going to be predicted to be not male. Let's take a look at how this model works. If we have indicators, indicators can only take on what value? Indicators can only take on what values? Indicators can only take on what values? So we'll say logit p. Indicators can only take on what values? Indicators can only take on what values? You're either right-handed or not right-handed. There's 0, 1 Boolean. I love those Boolean terms right there. 0, 1 Boolean. So Boolean is just like 0, 1, like binary operators. So these are the indicator variables right here. They indicate someone is right-handed or, so here I have indicated I am right-handed or I am not right-handed. I have indicated I am left-handed or not. What have I indicated? I have indicated right now that this person is not left-handed. I have indicated that they're not right-handed. What are they? What have I done? Alexander's double checking his work. Ambidextrous. Because if you're not right-handed, you're not left-handed, you're ambidextrous. They're like lights in a house. What do your parents say to you when you leave a room? Like if you turn on this light in this room, you leave the room. What do your parents? You've left the room. You're no longer right-handed. You've left the room. What do your parents say to you? You turn on the light, you leave the room, your parents say, "Hey, you're not in that room anymore." What do they say to you? They say, "Hey, that light's on. You're not in that room, though. You're not a right-handed person anymore. You're ambidextrous." They say, "Turn off the light." Think about this. Is such a thing possible in the way we work with indicators? Is such a thing possible? With an indicator for one variable, can we indicate someone is right-handed and we indicate someone is left-handed? Can we indicate someone is right-handed and left-handed? Not in the way that we're indicating it. We're saying ambidextrous. Can we do this mathematically? Do we do that mathematically? Do we do that mathematically? We do not. No, we do not. You're either right-handed or not right-handed. You're either left-handed or not left-handed. And as soon as you're right-handed, you're not the other things. Does that make sense to everybody? As soon as you're right-handed, you're not the other things. And then the way to be ambidextrous in this equation is to not be right-handed and not left, vice versa. So I think a lot of people were probably right-handed. So all you're doing right here is solving for this equation. It would reduce down to the following because that's a 0. So mathematically, you're just doing this right here, which is going to give a negative number. Now, what I instantaneously know about this, since it gives a negative number, is that this person is going to be predicted male or not male. What do you think? Since it's a negative number, is the intercept negative because you're... That is correct. Alex, great job right there. A person who is ambidextrous would be predicted to be female because the value of the intercept would be the prediction. That's worth 1,000 points. We're going crazy today. That is correct, Alex. The intercept being negative is kind of the coefficient of the, this right here would be a model if somebody is ambidextrous, and thus we would only get the intercept, which would lead to a prediction of female. But think about this. Right-handed people are even what likely to be male, apparently, according to the model. Right-handed people are even what likely. Remember that we just look at the sign. Right-handed, which is the coefficient we're working with, Right-handed people are even what? They're even less likely. So if we take right here and we solve, I think we've already solved for this, and we take this and go, so take a moment. I'm going to show you the value and solve for the probability now. Solve for the probability of a right-handed person being male. Okay, so take a moment. So is a negative logit, it's going to be below level of correct. All negative logits will have a probability of less than 50%. Ella, that is 100% theoretically accurate. Great job, Ella, right there. All negative logits translates to probability below 50% when plugged into the e raised to the 1 plus e raised to. This is what we're getting to right here. Can you now that you found the logit, solve this out? So we have the logit on the screen. Translate the logit into the probability, which is e raised to over 1 plus. I think Alexander's got it right there. So the equation, once you find the logit, is e raised to whatever that value is. Well, we'll grab the logit. And remember, that's what we solve. That's just your traditional solving an equation over 1 plus e raised to. And, oh, what did I do? Something's wrong. Something's weird. Do you see it? How did I immediately know something was wrong? I see it now, but I'll change it in a second. How did I immediately know something was wrong? Exactly, Ella. Good point right there. How did what clued in? And I was like, that's wrong. If you had this happen on the test, you go like, that's wrong. You immediately clue in above 1. There's right there. Ooh, wait, we're doing right-handed, right? People are saying different answers in the chat. Did I copy everything right? Can someone check my work? I'm getting different answers. I'm getting different answers than people. People might have plugged in the... Wait, what? What's going on? Something's weird going on. 1 plus e raised to over 1 plus... You raise the whole... It's not just the logit. Oh, wait, what? 1 plus e raised to logit over 1... Oh, my... I'm literally saying it. I wrote it out earlier. I promise you 1 plus e raised to the... There we go. So there we go. That was wrong. Thank you. That was actually in a real error. Sometimes I make fake errors. Sometimes I make real errors. That was actually a real error right there. So e raised to over 1 plus e raised to... Don't worry. I promise you. I know we're doing it earlier. We're doing it up here. E raised to over 1 plus e raised to... You can put it on your cheat sheet just in case you might get something wrong. If the logit is 0, then you do get the probability 50%. That is correct. And we do the negative intercept over the slope to do it. And great job, Ella, right there. That's worth 1,000 points. Correcting Brian right there. I actually made a second mistake, not on purpose. Sometimes those happen every once in a while. Okay. So let's make this a little more complicated to see if you can solve it. Ready? Let's change what we're predicting now. Let's use a different data set. Let's predict what is a good data set to work with. So let's go here to data EX. Let's predict the probability a team wins. Is it the NFL? Here's the NFL data set. Okay, so we're going to pick the probability of an NFL team winning. And so let me attach the NFL data set. Does everyone understand? We're going to predict the probability a team wins. There it is, wins. No, that's the amount of wins, not if they win. I don't know if we have a good categorical one here to predict. Oh, that's a bummer. Let me find a different one real quick. We could do the wine data set. Wine has stuff we can use. Okay, so let's do the wine data set right here. And with the wine data set, let's predict the quality of a wine. So we have high quality wine and low quality wine. Does that make sense? What is the level of interest for this? High or low? Be careful. What is the level of interest for the quality of the wine? High or low? What is the level of interest for the wine? High or low quality? What is the level of interest? High or low quality? Correct. Low. That is correct. I was like double checking my brain right there. Why is it low? Why is it low? Remember in logistic the level of interest is what? In logistic, oh, no worries, Alyssa, good practice. Remember, repeat, in logistic, the level of interest is what? In logistic, the level of interest is what? It's last. So in logistic, the level of interest is last. Okay, so now let's think about this. Let's say your wine has 2 units of sugar in it. Your wine has 2 units of sugar in it. Predict the probability of the wine being low quality. The wine has 2 units of sugar in it. Predict. Correct. Scrap sheet allowed. That is correct, Ella, right there. Double check. Everything should be in the instructions. I think I have it all posted right now, ready to go. It's all out. Exam posted. So predict probability of low quality. So use the same thing. You should get pretty good at this now to be like, let me try writing out that equation. I'll start writing the equation for you. Remember, try to do this as I'm doing this. That does look accurate. That looks accurate, Ella. That might be the prediction. I think that it is. I know it's about 50%. I did a quick sort of cheat solve in my head because the logit's higher than 1. The logit's like 0.12 or something. And so the logit's above 1, so the probability has to be above 50%. So that, Ella, that looks correct-ish. So what we need to do here, let's write the equation. So logit prob. Remember, we're solving the logit first. Great job, Alexander. And we're going to solve into it the intercept. Remember, this is only logistic. Don't do the logit for the non-logistic. That's just the usual. And then all we're going to do is plug in 2 for residual sugar. And there's the logit. Now make sure to do it properly. E raised to the over 1 plus E raised to the... What is wrong, man? I knew it. I hit it, and I was like, what am I doing? Oh, my gosh. There we go. There we go. I promise, as I was doing it, I was like, you're doing it again. You're doing it again. I'm saying it properly. So E raised to the over 1 plus E raised to the, just make sure to write down Y2. Oh, it just was a random idea. Because you could say, well, what about if it's like 0? And 0 is rather interesting because tell me, you now know if you plug 0 in here, that when you solve this, the probability will be what? Like if you're getting the theory down, so maybe, because we're all learning this at different levels. So this is just a hypothetical question to predict the probability when residual 0 is sugar. I can tell you for certain what? Predict probability of low quality for residual sugar at 0. It's going to be below 50% exactly, because if you plug 0 in here, then you're only going to get the intercept, which means you could literally take right here and plug the intercept in as the logit value, and there's the probability. Just to confirm, you could plug in 0, and you see you get the same value because you're just solving out the intercept at this point, and the intercept is negative, so that means we would actually predict a low-quality wine. So this curve, interestingly enough, is going to start a little bit around 0 and then go up. It's logistic up, but the start of it is going to be around 0 and then like around the 50%. And it's very hard to see. I don't know why it didn't graph it out all the way, but if it did, you would see there's a, like maybe there's just no wine with no sugar in it. I mean, there should always be sugar in wine, but that's what we expected to see and how the model was kind of making predictions. We were down here on this side of it. That was the first prediction Ella and Alexander put out there. But is this making sense right here that at 0 is the only time when it would dip below? There must be no wine with 0 sugar, hence the model didn't extend that far. But you can kind of see it at the small side of it. It's just at 0. I can't disappear. Is this making more sense, Alex? How to make predictions? Were you able to solve these along right here? Who has questions? Any questions right now? What are people thinking? We're about to do the next segment on AIC. So let me know what you're thinking. You're welcome. Great job, Alex. Let's head over here to the main screen. We'll do some AIC stuff. A little preview difference between screens. Got another hour and 10 minutes. Good time to do some AIC. And so let's talk about AIC. Thank you so much, everyone who is here right now. Let's head over to the main screen and do some AIC. AIC time. I have to give shout outs always to the man, the myth, the legend, Dr. Ake Ike. Been told I pronounce his name correctly, which makes me happy. It's tough. I always try to, we hear a lot of names and we want to make sure we get them right. And Ake Ike is not a very common name where I'm from. So, but students said, you are pronouncing it correctly because they actually know how to pronounce it. And I was like, yes! Hirotogo Ake Ike. There's the gentleman right there who created this. How many interpretation questions are on the exam? Something like there's like four-ish, I think, around there. It's a good portion of it, and we did some other stuff while doing interpretations there. So why is this important? Why does AIC matter? Why do we care about it? Well, AIC tells us how close our model is to the what. Like if you're looking for some stuff you need to know, AIC tells you how close your model is to the what. It's something you can't handle. We found a way to handle it in statistics. The truth. AIC tells us how close our model is to the truth. Now, if you think about that, would you like a large distance from the truth or a small distance from the truth? Would you like a large difference from the truth or a small difference? They go into all the big calculus mathematics that we don't even do. Ooh, there's AICC. You'd like a small difference. So the equations are rather interesting on how they work. When you look at the equations right here, there's a very important part of the equation. The very important part of the equation is the K component. The K component is the number of predictors in the model. This is AICC, which is Akaike's corrected criteria. So it's really just AIC, but it has this additional component right here. This is considered a penalty term. Like R squared adjusted has penalty on it to R squared. You do not want your AIC to be larger. So what would increase your AICC? Generally speaking, adding more variables you would expect if they don't help for AICC or AIC to do what? Because you don't want it to go up. So adding more variables, look at the equation right here. Mathematically, if the variables really don't help us, the AICC and the AIC, and they're virtually the same, very similar. They approach each other as n goes towards infinity mathematically. But they would do what? If you add more variables, a lot of times AIC will do what? If the variables don't help, especially, it will do this. If you add more variables, AIC would do what? It will get wetter. More x's, generally speaking, and the more x's that don't help. So KP, great answers right there. More x's that don't help, AIC goes up. Now, if an x is super awesome, it's going to decrease the AIC. Does that make sense? It's not always like if we add x's, AIC goes up. If we add x's that don't help, AIC goes up. So what is AIC trying to do for us? Just think mechanically with what we just said right there. If we add x's that don't help, AIC goes up. AIC is helping us select models. How? Just try to follow me on this logic that if you add x's that don't help, AIC goes up. So we're going to see higher AICs if we keep adding x's that are just because k is the amount of terms in our model. So if you keep adding junk terms, AIC is going to go. You don't want that. So AIC is helping us compare models to find models that what? In the words of Kingdom Hearts, simple and clean. What do we mean? Well, they're not going to have a lot of x's, but they're going to do really awesome. We're trying to find models that can reduce the sums of squared error, but also limit the amount of variables taken. Does that make sense? The goal in regression is to reduce the sums of squared error. But then we are also trying to reduce the amount of variables taken to not take too much information from the x's, lest we take a bunch of junk variables. So this is, in some ways, an alternative to R squared adjusted. It's the information school of knowledge in statistics. So how do we use it? Well, when we use it, we can use it a lot of different ways right here. First off, let's go ahead and make a model right here. Let's make a height, weight, plus gender, data, survey. There we go. And let's go ASC. There it is. What would I maybe need to start looking at this AAC and saying, does it matter? What would I maybe need? That's cool. That's in AIC. That's a AIC. What should I maybe get to start being like, is that a good AIC? Is that a good AIC? Is that any good? There's no interpretation of AIC. We don't say my model is 3,489 units away from the truth. There's no interpretation of it. It's just, how do we need something else? What do we need to start thinking about if this is a good AIC? Is that a good AIC? Well, we need some sort of metric to compare it to. How could we get another metric to compare it to? How could we get another metric to compare it to? Well, think about my naming conventions. We could do more X's. That's right, Alex, right there. More X's. So let's make another what? Let's have another what? Another model. Maybe make a different model, right? Let's compare it to a different model. See this model's AIC versus this model's AIC and see which one's better. So let's go right here. Let's make another model. Let's go right here and maybe add the polynomial relationship of this variable right here. So now we're bringing this to the second polynomial term, which adds a kind of a polynomial bend to the relationship. And so let's go here and look at the model. What do you think? I hate that it went into this zone. I'm not happy about that. Make this model. I thought it would do a good bit better. I'll tell you the boundaries here in a second. Ooh. Okay, which model's the best? Model 1, Model 2, Model 3. Which model's the best right here? I don't know. I'm too naive. Oh, Terry getting a Mubot quote. Terry has become... we're adding that to jokes right here. Terry, we're putting that in a joke and a quote. Terry getting a joke and a quote today. You crack me up, you get the quotes, even well, there's no quote. Sweet. Mubot now knows that. You can also call a random joke at any time. Terry cracked me up right there. Okay. So what is the poly function doing? The poly function, great question. Alex, keep those questions rolling. Keep them coming. The poly function allows for bends to the model to go into play. So when we make a linear model, it's going to be a line. When we add poly 2, like putting the variable inside the poly function, the x variable, we allow for a polynomial bend. Let's take a look at this right here in the kind of easier world to understand what the poly function does. Then we'll consider the AICs. And people were correct. It is model 2 to the answer to the previous thing. And it's model 2 because it's the lowest. More on how different are AICs in a second. So let's make a model right here where we just do weight for the moment. Just one category. Like let's do weight. Not weight, but now what we're doing when we do polynomial models is we're doing the following. So when we do poly third term, we're allowing for a model that has kind of a local min and local max because you're doing a third degree polynomial. Let me make this easier to see here by doing max order. And you can see the second degree polynomial a little bit cleaner right here. So if you notice right here, by doing poly 2, I'm allowing for a quadratic relationship on the weight variable. Does that make sense? So now there's an additional squared term on it that allows for the quadratic relationship. By going to poly to the third degree, which is what we did here, when we create the coefficient estimates in the model, we are now allowing for a coefficient estimate to the squared. That's no longer, is that? Oh, that's the AIC. There it is. Here's the third degree polynomial term, which is actually not significant. And you can kind of see that if you look at this output, that the third degree polynomial is not that different from the second, which kind of confirms that significance coefficient that we saw back in my... oh, do you just do a random... I don't know. Mubot, you're distracting me, man. Mubot, you crazy. So does this make sense to everybody here what a polynomial model is? Also, looking at this right here, we see that the third degree polynomial is not doing that much better. Also, the R squared adjusted has a very small difference. The second degree polynomial is doing better. Also, this output also confirms via AIC. We don't usually look at AIC in this output, but confirmation right here via AIC that this model is the best. So let's look at this model here briefly on the first, second, and third degree polynomial. And by looking at the AIC, I don't want to do that actually because we do R squared adjust in that output. It would come to the same answer either way. More on that in a moment. But let's just talk about AIC here for a moment. We can do as many questions as people have. What is N again that is sample size. So to Ella's question, in the AIC calculations, and this is showing AICC, as sample size goes towards infinity, as you get a very large sample, then the AIC and AICC would approach each other. Because if this goes towards infinity, this is the second penalty term. The second penalty term, if we go sample size towards infinity, then what happens to the second penalty term, Ella? As sample size goes towards infinity, the second penalty term would go towards what? So now if you have a infinity in the denominator, as we get larger sample sizes, the second penalty term would approach what? As Rock would say, it doesn't matter. It'd go towards 0. So basically, as n approaches infinity, AICC is AIC. So AICC is generally used for smaller sample sizes when you have a lot of variables or a smaller sample size. It matters more on smaller sample sizes. But AIC and AICC are the same concept of a model comparison. I think we can calculate. We generally use AIC, but I'm pretty sure we can go AICC. There it is right there. Is it going to run it for me? It's mad. For some reason, the AICC gets a little bit mad. It wants to take like a different unable for method, whatever. You don't want to do it? Well, then that's fine. It says no, so not going to do it. But we can still get the AIC. We'd probably just need to write the function, which we could probably write. I could like code it into R in a moment, but we're not going to do that right now. But that package, the VGAM package, apparently isn't constructed to take the model we currently have. It's mad about the format of what I'm giving it. But so AIC is in the choose order output. Exactly. We see it right here. And so why do we have it right here to do what? Like theoretically, why does it exist right here? Theoretically, why does the AIC exist right here? Why does the AIC theoretically exist right here? For this beautiful graphic. Why do we have AIC? There's also a question of why. Why do we have this? An easy scan of the output would make it really easy. Why do we have AIC right here? Why AIC? To do what? It goes back to why are we even doing this? It actually makes life really simple. Who knows? We use AIC to do what? It lets us know how close our model is to the truth. There's no interpretation. Kind of, basically, which model is the best? And we don't even know what the truth is. We're just estimating which model is the best. And when you look at this, to figure out which model is the best, you should find the what? To look at which model is the best, you should do what? I just wrote a quick code to figure it out for me. To figure out which model is the best, that's, I believe, arrange is in the dplyr library, I believe. It's in dplyr. FPP3 loads it up. More on that in time series if you want. To figure out which model is the best, what did I do? What did Brian code for himself right there, which you'd have to look through the output for? Rather than looking through this output, I just had the code do the work for me. I don't know how to make it do that. What am I doing right here? What is my goal in this? So think theoretically on this. The AIC that is the best is the one that is the whattest. The AIC that is the best is the one that is the whattest. The smallest. The AIC that is the best is the one that is the smallest. It's important to know also that AIC can go smaller and smaller and smaller and smaller. What is the smallest possible value of AIC? Great work, everyone there. What is the smallest possible value of AIC? The best possible AIC we would have when there's a complete reduction in the sums of squared error, perfect R squared of 1, AIC would be what value? Not 0. Interestingly enough, not 0. AIC goes to negative infinity. Negative infinity. So you can get, I think that oftentimes can catch people off guard when you get negative values of AIC. A lot of people are like, wait, what happened right here? So you can get negative values of AIC. We're not doing it right now because we don't have a good enough variable. I'm trying to think of a variable I know that's like a lot better that we can get to negative infinity and beyond. Exactly. So AIC and AICC can go to negative infinity. So the number one thing to know is lower is better at all points. So when you think about models, you just want to be like, is it lower? Now let's look at this. Brian just made a super complex model with tons of stuff in it. With this super complex model with tons of stuff in it, is this model a good bit better? So when is AIC a lot better? Is that one a lot better? So here's the AIC of this model with tons of variables versus the AIC of my best polynomial model. So is that AIC there a lot better? Is it a lot better? We do have a boundary we use. I don't like the gray zone, which I hit on the first examples I was doing. I was like, it's kind of iffy. Is it a lot better? I'm going to put about there because there's no defining lines for what is better. It's like, yeah, kind of. So exactly. That's, and it's is considered kind of a big difference, right? Kind of a big difference. Like, let's say your friend wants to tell you that they're better in basketball than you, and you play a game to 21 and they beat you by 2 points. You'd be like, eh. So if your friend beats you by 2 points, you'd be like, I mean, I don't know. I mean, maybe I'm better than you. You're better than me. They're like, but I beat you. And you're like, but this is from a sample. We played only one game. We have one game compared to my one game versus your one game right now. You beat me by 2. I don't really know if you're better than me. And they're like, well, you can't handle the truth. And you say, no one can. We don't know the truth in statistics. All models are wrong. Some are useful. But what if your friend beats you by 10 points in this game to 21? Bit of a big deal, right? Bit of a big deal. In the game to 21, your friend right now, I know it won't make sense, beat you by 327 points. Not even possible with this example. But that's a pretty big difference right there. That's something where we're like, yeah, that's a big deal. You can think of like a game to 21 where it's like a 2-point difference is like, yeah, it's not that much. But 10 point, like, that's a pretty big deal. So I might be like, well, what about a 5 point? Well, that's kind of a difference. I don't know. But these are the numbers we generally use to talk about what is a big difference. Because the whole point of the AIC is to what the AICs. The whole point of the AICs is to what the AICs repeat. Like, this is why it exists. The whole point of this number is to what them. The whole point of the number and getting this number is to what it to other whats. The whole point of it is to what it. The whole point of it, finding it, knowing of existence, great job Ryan right there, is to compare it. It's a model comparison metric to tell us how close our model is to the truth. And then between the ones we compare, we do want to minimize, great answer right there, Morgan. We do want to minimize the AIC, and minimization of the AIC is done by minimizing sums of squared error while minimizing variable selection. So the way to minimize the AIC is to make the best model that selects the least variables. So once again, variables increase it, and reduction of sums of squares error decreases it. So we want to select as few variables as possible while decreasing the sums of squared error the most. So a simple model that does a great job is going to get the best AIC. You could get a complex model that does really good because maybe your simple models are bad. But conceptually speaking, the models that get the best AICs are going to be the ones that do the most reduction to the sums of squared error, highest R squared, and they thus also select the least amount of variables. Double your decision of model choice when AIC is negative. Model 1 with AIC negative 50, model 2 with negative 100. Oh, exactly. So Terry writes a really good question right here. Which model is best? So let's go model 1. Model 1, AIC negative 250. So which model? Terry wrote a really good question right there in the chat. Thank you, Terry, for being here. Awesome input. Which model? Let's do 3 models. Which model here is the best? Which model is the worst? Take a moment in the chat. Terry's pointing some good points right here. Which model is the best right here? Terry's pointing some good stuff. Which model is the best right here? Model 1, 2, 3, 4. Those are all AICs. Obviously, it says AICC would be the same thing. It's just that it has the extra error term. And compare AICCs. Yeah, I think KP has instantly figured it out. Model 1 is the best, and then they are in order right now. Exactly, this is the lowest. And be careful. A lot of times people will, reverse it, especially with the negatives. That's very common error right there when the negative exists. Double check. And the worst is this. Most negative, exactly. If you don't have a negative, it would just be the lowest. So in instances when there's not a negative. And great job, Terry. Good questions, good checks of knowledge right there to make sure we have it. Any other questions about AIC? This has been a good segment on AIC. We're about to break into some model hierarchy next. Remember, you get infinite attempts on your quiz. Infinite attempts on your quiz. So I am going to do a question on the quiz and talk about model hierarchy, but you get infinite attempts. Infinite attempts. And we'll talk about some model hierarchy coming up next here on Stat 201. BAS 320, what are we doing? I don't even know. Let me get Word open. And then need to fix the computer a little bit later. I knew you'd open all my documents. I knew you would do that. My computer just doesn't like me. Computer. What did I do to you? I do not know. Okay, let's talk about some model hierarchy. And we got time for a few more questions. We're doing a 3-hour review today. Lots of great stuff. Thank you everyone who's here, everyone who's swung by. What questions do you have as we just relax right here? I think you can do the music, right? Yep, good. Okay, I'm logging into Canvas. Do a little two-factor. Drop those questions in the chat. Almost there. We had tacos last night. Tacos are awesome. I'm just thinking about lunch here in a little bit. I'm like, I can have leftover tacos. They sell, what do they call it? Tortillas that you can cook on your stove at HEB. Shoutouts to HEB. I'm sorry, Trader Joe's and every other place in Knoxville where you can buy groceries, but the one thing we will miss of Texas is HEB. Anyone who's from Texas knows what I'm talking about, or anyone who's been to Texas. Can you do the step function? Yeah, we could do step function next. How to find R squared adjusted, not from output? Oh, we wouldn't find it by hand. Ooh. Good question. Let's talk about R squared. So we got step function, R squared adjusted. We would not find R squared adjusted by hand. Understand it conceptually though. What do you say the students struggle with the most on topics? Logistic. Central market is amazing. Also got central market. Explain question 10 on the quiz. Oh, look at some question 10 right here too. We'll probably do 10 and 11. Let's check out 10 and 11. I'm gonna wake up. Try to wake up. Okay, 10 and 11, good combo right here. Okay, question 10 and 11 on the quiz. 09. 17. Let's go check out 10 and 11 on the quiz. Here we go. Let's go do it. Okay, remember you do get infinite attempts right there, all that extra credit. My Stream Deck is just not happy today. What happened to you, Stream Deck? Okay. So instantaneously, just looking at this question right here, I can tell it's dealing with what sorts of variables. Just when you see like all this 0-1 combo stuff, you can tell it's dealing with what kind of variables. There's a few others. I think maybe Chase, good question. You will do some work. It's working with a categorical. Great job, KP. It's working with an indicator. It does say indicator right here. And we have the seasons of the year. Now, what season will we not see from spring, summer, fall, winter? Is a categorical variable we're working with. What season will we not see from spring, summer, fall, winter, and why? Fall, it's the reference. Remember, when we do reference levels, the reference is first. That's not like logistic, because write down reference levels are first for categorical X's. Logistic is a categorical Y, and logistic, the level of interest, is last. So we have right here the three indicators. Why are there three indicators? Above is the interaction of the regression equation. The interaction is do we select these from a? Do we select these? Oh, let me look, Alex. Okay, let me take that, Alex. We'll do that next right here. Let me copy that. We'll do that next, Alex. I'll throw that in here between this. Maybe the instructor changed it, and so let me write that down over here, which is fine. Which is fine. I'll talk briefly on that. So I'll try to give some clues, and I don't know how your instructor has it set up, so I don't want to step on any toes. I've been shown hints right here for questions or working through some because there's infinite attempts, so I feel it's fine to just do some of these. Are the same, the order is different. Oh, okay, it does randomize the order? Okay. Okay, we'll do that one next right here. So good question right there. So good stuff, good stuff. We'll find that one here in a second. So, and then if someone said a model hierarchy one, we'll do a model hierarchy next. So I should know these are created, right? My brain needs to turn on. Okay. So when season is fall, what are the values of the other indicators? So it's saying we are at the what now. It is telling us we are on the what. When season is fall, you should interpret that as in we are making predictions for the what. We are making predictions for the what. We are making predictions for the what. Well, KP, KP, you got it right there. And the reason being is we are making predictions for the what. If it's fall, that means we are at the what. We have identified fall as the reference, correct. If you say 0 for spring, what are you telling your model? Talk to your model like it's a person. I am their model. Talk to me. You are telling me by saying season spring 0 that currently what? Like you're talking about season of the year, and if you say season spring 0, great job, Alex, excellent work. You're saying it is not spring, it is not summer, it is not winter. So that's what the zeros mean. And if it's not spring, it's not summer, it's not winter, it is fall. What if I told you right now, I don't live in, oh, I guess I can't. Decode this mystery. Brian says he doesn't live in North Carolina, Texas, New York, blah, 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 blah. And I say I don't live in any of these states, but I leave one out. What state does Brian live in? This is not true. It's a joke question to see if you understand the concept. But Brian says he doesn't live in Texas. He doesn't live in North Carolina. He doesn't live in South Carolina. Brian doesn't live in Delaware. Brian doesn't live in Wyoming. Brian doesn't live in all these. Is it Alaska? Very close, Alex. I will double check. I think it's Alabama. Yeah, it's very close on that one, right? It's Alabama. Why? Because Alabama's first. So, Alex, I even had to think, I think it's Alabama. And if you look at it right there, the state of denial. Apparently, that's the truth right there. But does that make sense? Like, if I listed all the indicators for states, another example would be, it's not that day right now. Oh, darn it, it's tomorrow. Tomorrow would be described in a model as not Thursday, not Wednesday, not Tuesday, not Monday, not Sunday, not Saturday, because tomorrow, the reference level being Friday, is not any of the indicator days. Does that make sense to people? We're just kind of talking over this one here to say, if there's 7 days of the week, how many indicators are there? If there's 7 days of the week, how many indicators? This is just review. If there's 7 days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, that's how they go. There's 6 indicators. What day of the week from Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday is the reference? What day of the week from Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday? That's how the days of the week go. The weekend, Saturday, Sunday. I promise you. Wait, KP, what's the reference again? What's the reference? This one, hey, great job, KP. That usually catches people because we do say Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And it's Friday. Why again? Repeat to me again why it's the reference. The reference when we do categorical X's, the reference is always what? This is our practice. Put it on your sheet. When doing categorical X's, the reference level is always the what? And we always remove one of these. So we got this right here. Great job, Morgan, right there. It's the first one alphabetically, and so we always remove one. In logistic, the level of interest is last, Ella. So logistic is for categorical Y's. This has all been categorical what's right here. This has all been categorical what's. And these are the small differences, sometimes where there's a little switch, where we make a confusion. These are indicators which are categorical what's-is. These are indicators with reference levels, which are categorical what's-is in the model. Not logistic. These are indicators with reference for categorical X's right there. These are categorical X's. So small difference right there. We'll hop over here. Remember, logistic is categorical Y. This one has only dealt with a categorical X idea. It might be logistic for all we know, but the idea of these indicators are categorical X's. Good job, Audrey, right there. Good practice. That's why we review it and do a lot of multiple times questions on it. The question was, and please ask any questions you have. Is this the one? I wrote it down. Wait, I wrote it down over here. I'll just do short run. Above is an interaction plot. Okay, interaction. Above is an interaction plot of the regression equation with an interaction term, salary, predictor from education experience, and the interaction. Cool, cool, cool. This is the salary data set, the Harris Bank lawsuit. Boop. Which one of the following interpretations is correct? Okay, cool. So I want you to think about this for a moment. We've got right here a plot, and let's take a look at it. Let's zoom in on this. Let's enhance it. Find Jason Bourne. And over here. Okay. Looking at this first graphic right here, we see these people have a low level of experience. Their experience is small. These people have the median value. And small means the 10th percentile. That's how the graphic's actually created if you look at the code behind it. These people have a large level of experience. What would the rock say about somebody's... Remember, we're talking about the people who have a large level of experience. What would the rock say about somebody's education if they have a ton of experience? What would the rock say about those people and their education? So now let's talk about these people's education. What would the rock say about that? If people have a very large level of experience, their education, you know what the rock always tells us. The rock would tell us, it doesn't matter. It doesn't. Why doesn't it matter? Because think about your interpretation. Two people who both have a large amount of experience, who differ in their education, are predicted to get the exact same salary. You have person A over here who said, I never went to school. That's cool. Person B said, I spent my whole life in school. They're Brian Stevens, every day in school. And they're predicted to get the same amount. They both have a lot of experience right here. Now, when you go down to the people over here, these people all have a what level of experience? These people all have a what level of experience now? These people down here all have a what level of experience? Those people right there all have a what level of experience? Now, oh, did we not save that? Uh-oh, we'll re-add that. It's gone. It matters is gone. They all have a small level of experience. And at this point, it really does matter. Now the differences are very large. And when you think about this, think about how if you don't have much experience, your education might matter more. Now, the way to always interpret every interaction just in a general way is to say the following. The way in which X1 explains Y depends on X2. So take a moment and think what the X's are, and let's just talk about this for a second. The way in which X1 explains Y depends on X2. So fill in this sentence. That's what I want you to do right now. Fill in this sentence. The way, and you could do it either which way with the X's, but the way in which X1, so you could start with education, explains Y, which is salary, depends on X2, which is experience. So think about that. How would that sentence be filled in right there? And then try to think about what it means. The way in which what? Let's fill it in and be like, okay, what does that mean though? So that's the general way. Like when we talk about an interaction right here, like X1 and X2 have an interaction on each other. What does it mean? Because we're making predictions on it from education right now, right? This model is a model predicting education. So the sentence would say, we'll wait here a moment for someone to fill it in. We'll see what we got. See what the answer is. Everyone's like, "Ooh, I've been reviewing a lot today. I need those coffee grounds," and they won't. Oh, no. I'm not getting them. The way in which education explains salary depends on experience. Exactly. Because for high levels of experience, education doesn't have a strong relationship. But when someone has a low level of experience, all of a sudden now it's very significant. Same thing over here, that someone, when they have a small level of education, experience really matters. Over here, when someone has a high level of education, guess what? Experience is actually a negative coefficient. I think of this as the education industry. Imagine you have a new PhD in computer science, or you have somebody, not age shaming here, but somebody who got their PhD, let's say 50 years ago in computer science. Which person do you think a university might be more interested in? The person who got their PhD and who's been publishing? There's so many other variables. But if you have somebody who just got their PhD and they don't have any experience, but let's say both people went to Harvard, great school. They both went to Harvard and they got their PhD from Harvard, and one person has a lot of experience and one person has no experience, but they're both top level education. Well, maybe, and counterintuitively sometimes for people, it might be the person with less experience getting more because they have such a high level of education that it's like they have the most recent, most relevant education. And so they have like a very like the best current understanding of the topic, educated by the best people. But generally speaking, for most people, experience is going to increase their salary. We would expect, we can't say cause and effect increase, but we would expect people who differ in their experience by 1 unit, the person with more experience, to have a higher salary. So let's see which of these sentences coincide with our understanding from this. Education doesn't change salary when experience is small. Is that going to be the right answer? Education doesn't change salary when experience is small. No. When experience is small, education has a strong impact on salary. Just experience small right here. The coefficient of the interaction term is likely, no. If the coefficient of the interaction term is 0, what would you see? If there is an interaction that has a coefficient of 0, what would you see? If the interaction is 0, then you would see what? If it's exactly 0, you'll see exactly this. If it's close to 0, you'll see close to this. The closer the interaction term is to 0, the more what the lines are. The closer the interaction term is to 0, the more what the lines are. Not quite flat line. So flat line is going to be a regular coefficient. In just the simple world, in Alexander, great answers right there. The interaction, this is indication of a significant interaction, what we would expect, significant interaction. So this is not significant. And this is significant down here. So the less significant the interaction, the more parallel. And by not significant, that would be a coefficient estimate. We'll put B3 right there, of equal to 0. And p-value equal to what? What would the p-value equal to for this? If it's a coefficient estimate of 0, you can divide it by the standard error to get the t-statistic. So the t-statistic would be the coefficient estimate divided by the standard error. And so what would the p-value be of this? It'd be 1. Great job, Ellery, because it's the least significant. And then as, I can't make myself disappear today, as the coefficient estimate gets a lot larger, this is just hypothetical, something like, let's say, 8, the p-value is going to approach basically 0. So this is going to be a more significant. And the more perpendicular the lines are, the stronger the interaction. So we definitely see right here that there is some sort of strength to this interaction. There's something going on that's probably significant. Salary always increases when experience increases. Nope. For large education, when education is large, salary decreases. So salary always increases when experience increases. No, the relationship depends on someone's education level. So the last one has to be correct right here. The strength of the relationship between salary and education depend on the... Yes. Which is literally, I didn't plan this out, but this is literally the answer right here that we wrote. Basically, the way in which is the strength, the way in which x1 explains y depends on x2. And you see right the word depends right there. The strength of the relationship between salary and education, which is a YX relationship, depends on the other. So depends on right there, key on experience. So the strength of the relationship, or the way in which the variables explain each other, right there. So this sentence right there was the answer to the question, but talking about strength. Someone mentioned the model hierarchy. Hey, good to see our friend. I can smell a nice chart there. Our friend from overseas. Hope you're doing well. You said things are going well for you. We always like hearing that. Model hierarchy right here. How important is model hierarchy to you? I'm gonna not tell you what we think about it. I want to hear from someone who uses statistics for medical stuff. They've said it multiple times, so as long as they're okay with me saying it, they use medical statistics. They've come and visited us here, and we're always glad to have them here. How important is model hierarchy to you? So model hierarchy, let me put a new section in this video. So the first things we did, what was it? We just did indicators and interactions. So, and then we're gonna do step function, and it's essential. Ooh, it's essential. So keep the model hierarchy. It's essential. Do not break model hierarchy. So what is model hierarchy? Model hierarchy is kind of the idea of building your house. I'd like to live in a 3-story house. We're including the basement here. So a 3-story house, including basement. That's how I do it. So Brian, patience nested in hospital. Oh, exactly. Oh, yeah. So you're, yeah, of course. Yeah, that 100% makes sense with your nested, probably doing some, that's good, some designed experiments or something. Cool stuff. This is the application right now if you're looking at it. Do they use a lot of statistics in medical? Is statistics very common? Nested in town, nested in country, exactly. So make sure to include those terms, right? If Brian wants to build a 3-story house, what does Brian need in his house? If Brian wants to build a 3-story house, I say, okay, so we say, well, Brian, guess what? We're going to build you this 3-story house. There it is. Here's your house. That's it. If I build a 3-story house, what do I need? Just think about it theoretically. I need money to build a house that is accurate. What do I need to build that house? What do I need? Let's just build the 3rd story. There you go, just your 3rd story. We'll do it. We'll build that 3rd story. Need a foundation. So what is the foundation? Bradley, great to see you here. What is the foundation? What is the foundation of it? So explain to me, well, if you build a 3-story house, you're going to need like you got your 3rd level here. So you got your 3rd level. So what else do you need? The 1st and the 2nd, right? So if we build a model that has x to the 3rd and x to the 3rd, excuse me, what is our foundation of this model? If we had a polynomial model where it has x to the 3rd power, what is the foundation of that house? And this is with polynomials. What is the foundation to the polynomial model? What's the first 2 floors of it? So we've gone from the example now to the mathematics of it. We have a polynomial model with x to the 3rd power in it. So the foundation of this house is what? x1, x2. Well, to the 1st and 2nd power. It's Audrey, 100%. Great points right there, Audrey. Said it correctly, and Brian misspoke. And we could call this the first x in the model to the 1st power and x1 to the 2nd power. Does that make sense right here that we are including the x to the 1st power and x to the 2nd power because we have x to the 3rd power? Removing one of these from the model would break model hierarchy. Now, I'm gonna hurt some medical people in the industry to say you are not required to do this, but it is encouraged. Some people believe it's essential to do this and to keep the model hierarchy, especially for interpretive models. It's more important in descriptive, less important in predictive. You have the choice to not do model hierarchy, though. That's key to say. AIC sometimes does not preserve model hierarchy in its selection, and we just did some AIC stuff earlier. So that's polynomials, but let's do interactions, which we were just talking about. Interaction. So if we're going to look at the interaction between Brian and Darren, so we got here Brian and Darren are brothers. So we have the Brian-Darren interaction. Who should we invite to our party if we want to see how Brian and Darren interact with each other? Just think theoretically. Got a party and we're like, I wonder what Brian and Darren are how they're gonna interact when they're there. They're brothers. Wonder what they're gonna say. Do they get along? Do they fight? What do they do? How do they interact with each other? We should probably invite what to our model? So if we're going to have a party with Brian and Darren and we want to see how they interact, if we want to see how they interact, we should probably do what? What theoretically would you do right here? You never know. we both have significant others. So what should you do if you want to see how Brian and Darren interact? Well, not invite more people. You want to see how Brian and Darren interact. So who should be at your party? Don't go too complex. Audrey, you're on the right track. We just want to see how Brian and Darren interact. Invite both of them. We should invite Brian and Darren. So now let's go from the abstract to what we're doing here. If we have x1 in our model, or excuse me, if we want to do the interaction between x1 and x2, what should we include in our model? Like, I want to look at the interaction of x1 and x2, so what should I include in my model? I want to say, I wonder if x1 and x2 has an interaction. Well, let's put that in the model. So what should we put in our model? If we want to see how x1 and x2 interact, what should we put in there to interact? What should we input into the model? Just go with what we just did previously. If we want to see how x1 and x2 interact, we should put in what? x1 and x2. Yeah, great job right there. Excellent work, Alexander. Another 100 points. Well, we're showing how to do this, but let's take a look. Maybe I'm on a delay today. A lot of people are responding at one time. The way it works, I made some changes to the streaming setup. I'm hoping it didn't break anything. Is if we want to predict someone's height from their desired weight, I think it's that, plus their... Does this model right here preserve model hierarchy? Does this model preserve model hierarchy, yes or no? So look at what I just created and respond in the chat. Does this model preserve model hierarchy? Really? Sure, why not? No. I like that. It does not. Why does it not? Why does it not do model hierarchy? Why does this model not preserve model hierarchy? Because this model just has in it the what. This model does not preserve model hierarchy because it just has in it the what. This model does not preserve model hierarchy because it just has in it the what. It does not preserve model hierarchy because it just has in it the what. Just about 10 minutes. It does not preserve model hierarchy because it does not have in it the individual x's by themselves. There's no desired weight and there's no weight variables. If you change the code slightly to the multiply, it actually carries model hierarchy through for you. So this is, well, we do have the interaction. This is the interaction term right here. And now we have the lower order terms. Comparing the output from the two models, make it a little bit smaller so we can get both on screen. You can see the original model only has in it, we don't need that graphic. The original model only has in it the interaction term, which is the x1, x2 interaction, where this model down here has the interaction term and preserves model hierarchy by having in it x1, x2. Does that make sense here? Let me know if everyone's following along with this. This model is said to preserve model hierarchy because it has an interaction term, and then it has in the things that make the interaction. So looking at it visually over here, you can see if we have an interaction term between x1 and x2, we need to then put x1 next to our model. So then how do you interpret the beta coefficient in the presence of a significant interaction? Oh, we were just doing that previously. So it depends, and you would have to solve the implicit lines. So when we do have a significant interaction right here, which is very important, we were just doing a question a second ago where we had a significant interaction, and right here you can see the interpretation of the beta term is going to now, or our beta estimate is going to now depend on the interaction. And the interpretation right here, in a very small sense, is the way in which education explains salary really doesn't matter. Because for high levels of experience, and we'll say we solved for an experience line that is the 90th percentile, when we look at two individuals at an experience level of 90th percentile, the expected difference in their salary for individuals who differ by 1 unit of education is about 0. Because the interaction right here is causing, it is mathematically, it's leading to where changes between individual or differences between individuals are rather small at high levels of experience, where at very low levels of experience, the differences are rather large. So the best way to interpret those for interactions are to solve implicit lines, because when there's an interaction, the differences are not what? And this is a very important thing to see here. When there's a significant interaction, which is the exact thing mentioned in the comment, the differences between individuals are what? When there is a significant interaction, the differences on the X are not what, which is the thing, the problem. When there's a significant interaction, the differences on the X variable are not what for the Y when you think about the XY relationship with the other X. They're not what. Think of a C word. The differences between the individuals on education for their salary are not what? Because they could be this, they could be this, and actually there's infinite lines when you solve out the implicit lines. There's not a constant or consistent difference. So the best way to get the answer to kind of, there's not a consistent, does that make sense? Like, is the difference this? Well, is the experience level small? Is the difference this between individuals? Well, is the difference the median? Like, are the individuals at the median level of experience? I think the L coefficients are not interpreted as the units in that's the biggest thing. It's harder to interpret when it comes to interactions, and sometimes your best way to think about the interactions is to simply visualize it. Like, if you can make a visual for models that are not too complex, probably best to visualize it, because sometimes the interactions, if you have a lot of interactions, then it might not actually be that interpretable, especially if you're looking at like a three-way, four-way interaction. At that point, it's the way in which X1 is explaining Y depends on X2, depends on X3, depends on X4, but the coefficient of X2 depends on X3, X4. Like, you're reaching high levels of interactions, at which point we might say we don't really have good interpretations, we like to interpret stuff as best we can, but sometimes the descriptive model is harder to use. No, that's good points right there. Or stratify and run 2 regressions. Gosh, you know these super advanced stuff. I always love your advanced questions. That's so good. We have one more way of looking at hierarchies right here, or hierarchy in modeling. The other way to look at hierarchy, which is very important, is when we talk about hierarchy when it comes to indicator variables. So when it comes to indicator variables like, let's say, season of the year would lead to how many indicators? And indicators are categorical X's, and season of the year would lead to how many indicators? We have fall, summer, spring, winter, maybe in that order, maybe in not that order, preferably winter. It's going to lead to 3 indicators. And how do you know how many indicators there are? How do you decide how many indicators there are? How do we determine the amount of indicators? If we have 4, why is it 3? Because there's always one what? There's always one reference level. The indicators are 1 minus reference level. There's always one reference. And why fall? This is repeating. Why fall? Why do we choose fall as the indicator? Why do we choose fall? Oh, choose fall as the reference. My brain said boop, boop, boop. Because the alphabetical order is just that arbitrary. Now, you can do what's called relevel, so you can reassign it. There is the way to do that, but by arbitrary assignment, we assign it to the first alphabetical. You can choose another one, but it's not the default, so we keep to the default. It doesn't matter, actually. Yeah, exactly. We just need something to compare to. But the algorithm chooses the first alphabetical, but we could always reassign. It's like, why is it the first alphabetical? It's just the name we gave the season of the year. And so now when we think about this, let's go right here. And what we're going to do, there we go, is we're going to think about a model right here. But this model only has season summer, season spring, and that's in the model. That's all that's in the model. what do you notice about this model right here? This model has coefficient estimates. We could pretend we're looking at some output right here where it says estimate, and then it says standard error, and then it says t-score, and then it says p-value, and we'll come up with some fake values here for this in a moment. But what's weird about this model right now? What's weird about this model? What's weird about this model? It's like, it doesn't follow our rules for model hierarchy. Why? Model hierarchy with indicator variables say, if you have 3 indicators, you need to do what? If there's 3 indicators, to preserve model hierarchy, you need to do what? It's as simple as it sounds. If there's 3 indicators you make what? This model has not done that. So it did not preserve model hierarchy. If you have 3 indicators, when you make your model, you make... I promise I'm not trying to do a trick question. We should include winter, right? So if you have 3 indicators, to preserve model hierarchy, we should have... We don't want that big. Oh my gosh, what have we done? Watch this. If you have 3 indicators, you make 3 indicators. Now we've preserved model hierarchy. But removing winter does what? Now we still have to make predictions for winter. We still have to make predictions. So where does winter go? Winter now becomes part of what? It has to exist somewhere. Where does winter exist? Boom, right there, Alexander knows. Winter becomes part of the reference level. So now winter is now, or fall rather, is the fall-winter reference level. If it's not summer, if it's not spring, it's fall or winter. So we have 3 levels here where the reference level has now taken on winter. But let's think about how these T ratios, I'm trying to think if we have output that does this. Let's do a few kind of, we've covered model hierarchy here. We'll do step function after this little brief segment on coefficients and interval estimates. So coefficient interpretation. Coefficient output interpretation. Coefficient output formulas. Okay. So what you should be able to do is you should be able to tell me the remaining values in this table. Let's go right here. Assuming the sample size isn't tiny. Make it a little more interesting. Okay, let's put a value. Dummy variables. Yes. Classic coding's going to do them as dummy variables. We get them assigned for us for free. Okay. Think of this. Who knows values A, B, C, or D? Can you solve any of those variables? Sometimes the T is called a T ratio. Standard error is your uncertainty. Who knows any of these right here? Any of these? Any of these A, B, C, or D? So how can I get the p-value? Well, we'll see that in a moment. I don't think we have any find the p-values on the test. A is... double check, Ella. I think I know what you're doing, Ella. What is the T ratio? So if something has a 0 estimate, what's its T statistic? The T ratio, the T statistic. Give this a moment more, see if you can find any of these. I'm trying to come up with some really tough questions with good theory on the output. So don't worry if you're like, I have no idea what's going on. That's all right. Some people take some more guesses. If you say something has a coefficient of 0,
it doesn't matter.
Can you tell me the p-value? If something has a coefficient of 0, can you tell me the p-value of it? I think it doesn't matter. It's pure. You know what's gonna happen. Audrey, you're on the right track. Oh my! Oh no! Oh no! 2 seconds. If this video gets copyright claimed, that's my fault. The Stream Deck has a problem right now. I usually play randomness for a second. We got copyright claimed on one video by Monstercat. I'm sorry, my Stream Deck's not working. Please don't copyright claim us, Monstercat, because they'll monetize the video. That's not my goal with these. I don't monetize these videos. I monetize like little fun things that I make that I spend like a weekend making, and then I might make $10 that we give away on Amazon. We give away the Amazon prizes with that. But it's not my intent for this video to get monetized. Hence why I was like, I got to get out of that screen. I was trying to get away from it. Put randomness on every screen. I had to go over and deactivate it on its own thing right there. The Stream Deck's acting weird today. It's can't click the random button. Don't do it. Randomness is turned off. Click the random button. Not happening. Okay. Yes. I think we have right. Well, so let's look at the answers we got. So if something has a coefficient estimate of 0, I'm telling you it's not what? Anything that we're saying is 0 doesn't matter. So it's pure randomness. It's like, it's 0. It doesn't matter. So at this point, it's not statistically significant. That is the least statistically significant coefficient you can get. Any sort of relationship is like, I don't know, it could be positive, could be negative. But what is the T ratio? The T ratio is always your estimate. Here, we'll highlight as we're doing it. The T ratio is always your estimate what? The T ratio is always your estimate what? It's a ratio. So what do you have right now to work with? It's always your estimate divided by your uncertainty. So what is the T ratio there? What is the T ratio? Who can solve the T ratio? I think Morgan got it. Morgan, great job. We'll start at 100 points. Morgan said it's 0. The T ratio is 0 because it's the ratio of the two numbers. If you do this by classical statistical methods, if you go and find the p-value now, it's actually that it's greater than absolute value of t. And so we're looking at the p-value for the greater than absolute value of t. If you go to any t curve and go to the center of it, you would actually be shading both sides. And what percent of this curve have I just shaded in? Who knows what percent of this curve I've just shaded in? I've just shaded in, say it with me, 100% of that curve, because we landed at 0. The t statistic right here is 0. We landed at 0, and we're shading outside all the curves. So we're saying, I mean, if there's no relationship between this variable or difference from this in the reference, because we're comparing it to the reference, then we'd expect a coefficient of 0. I saw exactly a coefficient of 0. That's the most likely to thing if I expect a coefficient of 0. If the null value, which is the hypothesized truth, if we hypothesize that 0 is the true value and we see 0, well, that's the most likely thing to see. Now, the T ratio, I think Alexander, great job, got C. It's still the same mathematics here. The T ratio, and we could still leave 0 there at the null. So 0 is still here as the null hypothesis, and the T ratio for how is the value of C found? Who can show me how to find the value of C right here, which is 20? I don't know how to type. I really don't know how to type. Who can tell me how that value is found mathematically speaking? Take a look at the formula right here. Great job, Alexander, right there. It's 20. Now, most of the time when we do T curves or Z curves, now do remember T depends on degrees of freedom, but as long as the sample size here isn't ridiculous, maybe even if it is like 2, maybe a ridiculous model, for most intents purposes, the T looks like the Z. Does anyone know what the answer D is? The p-value is going to be about this. For all intents and purposes, the output's going to show a p-value of about this because we are way off the curve. We're all the way, the 20 right here is somewhere over here, and we do negative 20. We're all the way over here. And the p-value, great job, Alexander. Yep. The p-values are those. That's the p-values. So
It doesn't matter.
It's 0. For all intents and purposes, the p-value is 0, and that's a statistically significant difference from the reference. Do realize we are doing indicators. So that's how all the values would be found right there. So we do see the relationship that when the t is larger, and what would happen right here if I did this to the p-value, and just look at the way it's formulated. What's going to happen to the p-value here if I have a t of negative 20, which the graph still looks the same, which is the answer to the question. If the estimate was negative, 10, would it matter? Would it change anything? The graph's still going to look the same when if we were to find this by hand. The answer is it doesn't change anything of what we do. We still get the same p-value of basically 0 because we do the absolute value of it. So by doing the absolute value of t, you're seeing just as extreme. One last question right here. This is our tougher question. We are trying to do tougher questions. Create a confidence interval for both estimates. Create 95%. Create estimates of. Assume decent sample sizes. What is that is the p-value, the probability, the significance, the p-value. There's no real formula for it, and that's probably not one that's really good for test questions. I gave theoretical ones that you can find because if it's 0, then the p-value has to be 1. If you get an extreme t-statistic, extreme t-statistics are going to have p-values of basically 0. A tricky one would give you... we would never put tricky ones on the test. Just understanding that the t has a relationship that the further away it is, the more significant it is. Like more extreme t values are going to shade less of the curve. Giving ones that are in between that you'd have to actually calculate are not something we would do. I think Ella just did it. Ella, yes, Ella knows the trick to this. Ella, how hard was this on a scale of 1 to 10? Because someone's looking at this right now and saying, how in the world did Ella just figure out both answers like that? What do we do right here? And it actually goes back to the curve. The curve right here can be used to create a 95% confidence interval. So let's bring the curve back up here a little bit and explain how this curve is going to now be used to create a 95% confidence interval. When I say 95% confident, what number jumps into your head? If I say 95, there's a certain number that we learn from Stat 201 that jumps into our head. What number? Alexander's got the equation. We should hear 2 because 68 is the empirical rule, 95, 99.7. .95 is the most common, and it's 2. So usually we use 95 because it relates to a 0.05 alpha. So you're basically doing, as we talk about in 2-1 a lot, the confidence interval with a hypothesis test with a confidence interval. So all we need to do right here is take our estimate, and we can just put the estimate in the center of it. We'll keep the z-scores on there, or t-scores technically. And we just got 2 standard errors. And technically standard errors, and Morgan, you are correct. Usually we think of it as standard deviations, but 2 standard errors technically, as Alexander has the formula in the chat. So the more interesting one right here is the 10. If you were to go right here and put 10 at the center of your interval, or we'll do 10. I made it -10 at the last moment. Oh, you did the negative. Okay, well, let's do the negative. Then you would go up, because they got to go up, -9.5, -9, down, -10.5, and -11. That's fun right there. Does that make sense to everybody? That you're just going up and down 2 standard errors. So you can just, Fisher just woke up and said, oh, Ronald Fisher, good old Ronald Fisher right there. Yeah, I guess, was he the one who decided the 0.05 alpha? Ronald Fisher? He did a lot, and he didn't like William Gossett with Gossett's tea. He wouldn't publish it, hence why Gossett didn't name it the Gossett tea. It's the student tea, his pseudonym. Ronald Fisher was not a fan of Gossett. Why? I don't know. But the other one right here, all you're doing is adding 2 standard errors right here. So the formula, if we write it out, is going to be our estimate. And then we go plus or minus 2 standard errors. So we take the estimate of 0 and go plus or minus 2 times 2.3. And that's where we get the interval. He was the mantra for Bayesian. He didn't like the Bayes stuff. The good news is that the reason we do the estimate, the reason we do an estimate right here is take what current model do I have stored. We'll do one more of these solves right here, and then we got a few more questions. Solve for me just very quickly an estimate, the upper bound for desired weight. Solve it very quickly, and I want you to round it to 1 decimal. Solve the estimate of for the 95% confidence interval for desired weight. Solve about to the estimate. Just do it in your head pretty quick. I'm liking it because it turns out to a decently neat number. And then let's show how we got that. Who knows the estimate of the upper bound for the interval? And then we're going to show how we got it. I'm not going to show the answer yet. But who has an estimate for the upper bound for a 95% confidence interval? Just use the same theory right here that we were just practicing. It's Alexander's carrying all the decimals. I was going to say 0.2. And the lower bound I'm estimating is about 22 minus 5.7. There we go. Those are my estimates. And take a look. Literally almost to these were my estimates. And what did I do? All I did was take the standard error. And this is me doing it in my head, remember. My estimate in my head, here's the actual numbers, are my answers down to, and that rounds up. So I did get that one right there. And then this one right here would be this to 3 decimals, rounds down. How close was I in my estimate that I did in my head? This is the point of why we just estimate it, sometimes looking at it and understanding the relationship it has. I was within a thousandth, not 10,000ths, of, I got one answer right to 3 decimals, and I estimated the other one within a 10,000ths. Because all I'm doing is taking the standard error and timesing it by 2. I turned this into 22, and I should have just done it the right way. I turned that into 22, and then I just added it in my head right here to this, and I said, oh, that is virtually, oops, wrong value. That's that. I was like, oh, that's kind of neat. And then all I did was take, and what 0.22? And there's the second number. So that's how I got, I guess I was nice on the rounding, but got lucky. But that's the second number there. So those should have been my estimates right there. Oh, yes. Oh, we should talk about that. Let's put that section in here. That's a really good segue, because what matters and how are we going to do this? Then we'll do step function and R-square adjusted to end the video. But what do we need to do? So everybody, we've got a way of doing this. How are we going to look into this and see if our assumptions hold? So let's do this. What do we need to do here? How can we do this? So under the assumptions of linearity, normality of residuals, and a third one, not just the normality of residuals, but the equal spread of residuals, known as homoscedasticity, not heteroscedasticity, which is unequal spread. So the equal spread. So we have some things we need to look at here. And how can I do that for my model? How can I do that? What do I need to do? Who can help us out? And what do we need to look at to see is this model the right idea? Should I even be doing this? Why? Is this good idea or bad idea? We're doing linear. So is this a good idea or a bad idea? It's a really good segue. Great. These are the real questions. This is the real stuff. Check regression. Let's check our regression. Boop. This exactly. So what do we see right here? Well, first off, how many conditions do we fail? We got 1, 2, 3, 4, 5, 6. We've got linearity of an X, of an X, of an X, the interaction linearity, overall model linearity. We've got equal spread, which is the check to see if we have homoscedasticity versus heteroscedasticity. And then we have the normality of the residuals. How many conditions did I say pass or fail? You might have to remind me of which one I said. How many conditions do we pass? How many conditions do we pass? I can't remember which way I put it, but you tell me. How do you look at this output? What does it mean? The null hypothesis, in general terms, is we're good. And Alyssa, great job right there. We pass 1. You'd say, well, I thought low p-values are good. Low p-value just means your results are statistically significant. The null hypothesis for this, when you do a check, is that everything is good. We assume linearity is good. For the first X, for the second X, for the interaction, for the overall model, we assume good. So what are you doing right here to the idea of linearity being good? Low p-value means you're whatting that idea. So I say to you, I think linearity is great for desired weight. And you say, Brian, I what that thing you just told me. You told me you think linearity is great. That's what you're starting out as. I what that idea. I say, I think linearity of desired weight is great. That's what I'm starting out believing. I'm your null hypothesis. Brian, I what that idea. In classical statistical sense, that idea you just told me, I'm whatting that idea. Think when the p-value's low, what the null. When the p-value is low, we what the null. When the p-value is low, we reject it. So you say, Brian, I reject that idea. Now, be very careful. I'm going to please say it correctly. I'm fine with two phrases right here. I say to you, I think the equal spread of the model is good. And you say, okay, null hypothesis. I what? So right here, yes, power. I'll mention that in a second right here. I'll mention that after this output. That's a very, especially with a lot of normality conditions. And that actually is why we do this. So you're going to see the reason. And I love that you're about to see what we do here and why, because that's the why of it. So what would you say to me here you say, I come to you and I say, hey, I think the equal spread is good. So what do you say to me? I what you? I what? So now that's a high p-value. So what do you say? I say, I think the equal spread's good. You say, you look at the p-value and you say, okay, what? What do you say? We'll see what people say. And then this leads into our next thing. I fail to reject that, which is the same thing as saying I do not reject. And I'm fine with either way. Classical stats says I fail to reject. Great words right there, Alyssa. That's how classical stats is always going to say it. I like to say I do not reject. Yeah, it seems like that's reasonable to believe. You could say that. Like, our model is a reasonable reflection of reality when it comes to the equal spread of the residuals. I do not reject what you're telling me that there is equal spread. The idea of fail to reject is the idea of not doing something. Think of this. I failed to go to the mall today. I did not go to the mall today. Maybe I will. But at this point, I have failed to go to the mall today. So I have not gone to the mall. By saying fail to reject, you're saying not reject. Because you either reject something or you do not reject something. You do not accept things when we do statistics. You either reject or do not reject an idea. So what was brought up right here is when we have a larger sample size, these tests get really powerful because they can detect, because nothing's right. All models are wrong. Some are useful. So since all models are wrong, our model are probably going to fail when we get to larger sample sizes. So if we fail a condition, we have to ask how bad it is by doing what? If we fail, like normality of the residuals, which is right here, we have to ask how bad it is by doing what? So because the problem is when you have a data set with 1 million observations and every stat that you run it's significant no matter what, you're failing all your tests. Now you have to ask how bad it is for that million data observation by doing what, which we're doing right here if you're doing this. You have to ask how bad you failed the condition by doing what. You're like, okay, I failed normality of residuals right here. That's the failure on normality of residuals. We have a problem. So you say, now I need to what? Now I need to what? Code tells you. Now I need to do what? Now that I've failed it, I need to go and do what? I need to check my plots. I need to see how bad did I fail it. Exactly. Oh, Batesman? Oh, I haven't done Batesman forever. Put in the chat what that is again. I cannot remember. Oh, Bayesian. I was like, Batesman. I was like, that's something that does not, I was wrong. I don't think I've ever done Batesman. But Bayesian, just change your whole school of thought. Switch from classical methods to Bayesian or information school. So now we need to check our plots. And also, when you look at this, bit of a problem right here. Bit of a problem. Equal spread, we didn't fail. Linearity, I'm not so concerned about. There's an extreme point over here, which is also going to hurt our, I can't disappear, sorry, currently. But there's something like Batesman. Oh, too many statistician names that exist for me to be like, Wilcoxon sign, rank, all these different things. Just why don't they call it the sign rank test? Someone's got to put their name in front of it, right? I thought it was like a transformation, like a box Cox or something with Batsman. That was like Batman for a moment. So now, how about this though? Let's change this. Oh, let's make a real change right here. I'm switching to what right now? Who knows what I'm switching to? You should know this as I change the code. As I change the code right here, what have I done? Say, Brian, what are you doing? I'm now doing a what? Had to do a few more changes, and that's very indicative of what I'm doing right there. What have I done to my code? What am I doing right here? What's going on? Statisticians do, except for Gossett. What have I done to my code right here? What have I done? What have I done? All of it is indicated right here. What have I done? Now we've switched. We're not doing linear anymore. We're not doing linear stuff, so we will not get any of this. Not going to get any of this. We're not doing linear anymore. Now we have a categorical. We're doing logistic. We had to change it to a binomial, two-level, logistic, and now let's check out the check regression. Here we go. Yeah, iterations usually do stuff like that. Ooh, is this good or bad? Just start me off on here. Is this good or bad? What do you think? Good or bad? Can we get some good or bads in the chat right here? I'll throw out some 100 points. Can we get some, is this good or is this bad? What are your thoughts? You're like, that's pretty good, or that's pretty bad. What do you think? Good or bad? Both are good. That's it. Both tell us that the logistic model here is a reasonable reflection of reality. You'd be like, oh, that's a little low, but Ronald Fisher said 0.05 is all right, or above 0.05. Now remember, when we do check regression, this is a big note for your cheat sheet, the one you can actually use, don't cheat. But p-values above 0.05, it's bordered. Yeah, it's like, but the thing is, this is good. If you keep to a consistent standard, you say if it's above 0.05 on the check regression, it's good. 0.05, 0.05, Morgan. Good work right there, 0.05. 0.05 is the classic alpha used by most statisticians. You can change your alpha. You could have a higher standard or a lower standard, but that would change your type 1 to literally is your type 1, type 2 error rate. Okay, I think we have a few more of the step function and R squared adjusted. This has been a really good review video right here. Really good review. I'm going to fix my... So we'll post all the things to this in a moment. We'll do a little section right now. What is the step function? Get ready here. How's everyone doing today? Is everyone having a good first day of exams? I think some people have the exam today. Got 2 more sections, but throw those questions in here. When will the Kahoot be? Oh, shoot. Let's do the Kahoot right after this. Okay, let's do the step function, and then we have the Kahoot. Our friend from overseas, you should play the Kahoot with us. I did say we'd be doing the Kahoot, right? Woo! So let's do Kahoot. We'll do prizes. $30 first prize, $20 second prize, $10 third prize. We'll get ready here. Give me a second. We'll do step function, and then we'll go into the Kahoot. Thank you, I forgot. Step function, let's do it. Here we go. Tell everyone joining in. Kahoot's about to start. Okay, so for the step function, the step function is an alternative to doing what selection? The step function is an alternative to doing what selection of models? The step function is an alternative to doing the what selection of models? The step function is an alternative to doing the what selection of models? The step function is an alternative to doing the what selection of models. We could just consider what, which can be intensive. Reg subsets, which is all possible models. Correct, Alexander. Reg subsets is the way to do an exhaustive search, which is all possible models. So reg subsets is going to look through every possible combination of all x's. Like, let's say this data set right here has, 12 quantitative x's and one categorical X that has in it 4 levels. How many possible models? So if we had here 12 quantitative X's and one categorical X with 4 levels, how many possible models are there? So there's 12 quantitative X's, like desired height or desired weight. We're predicting height. So desired weight, all these different things. And then there's one categorical X with 4 levels, like freshman, sophomore, junior, senior. So that's categorical X right there. How many possible models are there? You can tell me the equation. We're just trying to think through how many possible models would there be to consider. How many possible models are there? Like, basically, not combination close. Is that it might be that. It is the combination of 15. Well, if you're thinking of like choose, like it is permutations. It is, and there's a quick way to figure it out. The way to think about it is if you go into your kitchen and you have 15 items to make a cake with, you could choose 2 items, all combinations, 3 items, all combinations, 4 items, all combinations, 5 items, all combinations, 6 items, all combinations. That really gets complicated. Let's do the most simple thing first to talk about this. This morning, I've got 2 things. This is all I have in my kitchen. I have item 1, coffee. I have item 2, creamer. How many drink options does Brian have? Now be very careful. Great job, Alexander, right there. How many, this is not interactions. This is without any interactions, which you might say if you put them both in, isn't that an interaction? No, we're just putting them both in. Without interactions, how many drink options does Brian have? Usually people forget something, and we'll see this when we do the math, which Alexander's showing. Without interactions, how many drink options does Brian have? And this is just X1, X2. This is a 2X model. And great job. Both our people figured out the 15 for the previous one. So how many drink options does Brian have? Let's try to list them and think about what Brian could choose to drink this morning. Brian right now has how many drink options? I have 4. That is correct. And you might say, well, wait a minute. Why do I have 4 options? Usually people get the 3 options. We'll find the 4th in a second. First option is 1. We'll do 1. Option 1 is I drink coffee. Option 2 is I drink coffee and I drink creamer. Option 3, or I should have done it. Sure, why not? Option 3, probably a less desirable one, is I drink creamer. But what's the 4th option that people often forget? The 4th option is I don't drink anything. The 4th option, when you think about it mathematically right here, is the want. So nothing. Let's change these to x's right here that would be included in our model. So we'd have x1, x2 model, x2 model, and the 4th option is known as the what model. So if we consider an x1, x2, we're looking at all the combinations without interactions. That balloons things out of control. The 4th option is known as the model with no x's, known as this term. What do we call it? The model with no x's is known as the what model. I think autocorrect might help me. Yes. Known as the what model. Who knows? Good thing to know. 100 points in the chat. I don't... Oh, we gotta do Terry and the jokes. The jokes. Terry right there with some jokes. I was like, Terry knows it. The naive. I don't know. I'm naive. Mubot. The I don't know model. It doesn't have any X's. It doesn't have any information. And our friend right there is correct. It actually uses the mean of the Y. So the naive model is the mean of the Y. And if you look at it right here, the naive model, if you do a summary of it, it computes a consistent value. And that value right here, this intercept, is actually the mean of the Y variable. So the naive model is a flat line, which is the intercept. And so we call it the naive model because it doesn't use any X's. It has no X information. It's naive to the world. So now we get to what is the idea of the step function? Well, we could just consider, exactly. And we could just consider all possible models. But all possible models would be 2 to the 15th models. And this is without interactions. Well, we could maybe do that. This is possible. You might say, why is it 15? Well, each quantitative X introduces one coefficient estimate. As we talked about with indicators, if there's a 4 level, it would introduce 3 indicators. So for indicators, it's levels minus 1 for the estimates it includes. So there's 3 indicators that could be included. But what if we up this to 18 X's? Well, now if we have 18 X's, we'd have 21 coefficient estimates, and look at what happened. Now we have to look through 2 million such and such models, and it's going to keep exponentially growing. This has not included interactions, which would exponentially grow. Oh, and yes, we might be overfitting, which is why we should compare some AICs for this. And this class doesn't do validation holdout, unfortunately. We covered that in 474 with validation holdout, which is super important. More on that in 474 when you do model building. So now that we have this right here, let's look at the step procedure. The step procedure has some important arguments in it. When we look at step right here, we need a starting point. I'm going to start with the naive. That's saying I want to look starting at the naive. I'm just going to start my road trip on the naive right here. Then I need to give it a scope of which models it's going to look through. We're going to say the lower bound is the naive. Now, I'm purposely going to do something weird here when I get to my direction I'm going to drive. So these are like fences right here, saying you can do as small as the naive model or as high as the upper model. But when I go to the direction, I want you to think about what's going to happen. I'm going forward. Oh, excuse me. That's the way I want to go. I'm going to go backward. If I go backwards from the naive, The naive has nothing in it. What's the problem here? Visually speaking, we're searching for models. We're down here at the naive, and we're asking, what variables can we consider to go towards the full? The direction is the way we drive, and I have selected to go backwards. What do you notice with going backwards is the problem on the step procedure? If I go backwards, I got nothing in my model. So driving backwards from the naive will do what? Driving backwards, because I'm either going to go forwards by adding variables or subtract variables. So this has no x's. This has all x's. What's the problem here? What's the theoretical error? Backwards selection on the naive, what's the theoretical error? Let's see if anyone knows. I mean, you can do it, but it's nothing going to happen. Why is nothing going to happen? Because if I'm at the naive, and my choice is to tell it to consider removing things, so I'm saying, let's look at the code again. Start at the naive, consider models contained between here and here, like between this and this are your boundaries by which you can select. That sets the boundaries right there we were looking at. So that's the lower limit, that's the upper limit. This is my starting point, and I'm saying select backwards. So first argument sets your starting point. Second argument, the scope of list is the models to consider selecting through. And then the direction is the way in which I'm either adding, removing, or choosing to add and remove variables. Well, the problem theoretically here is I can't remove variables if there's no variables in the model. So what do I get for my final result right here? I get the naive. So we shouldn't do this. We should go forward from the naive or both direction. And when we go forward, exactly. Now, good questions right here, and this goes to tidy models, which is something 474, because with this right here, we are considering AICs. So we are not actually considering the significance of a model right now or the significance of a variable. We're only looking at, does it reduce the AIC? So in your final model, you can very well get things that are not statistically significant. So this is the final model right here. And let me look at it again. We might not have gotten something that's not statistically significant. We do. We have two variables in this model that are not statistically, that's not our step model. We have multiple variables in this model that are not statistically significant. I said multiple, and it's actually only two. So we were trying to predict somebody's height, I believe. And we have two variables that are not statistically significant. Because, and this goes back to the concept of AIC, when we did the step procedure here, it was comparing models and trying to optimize AIC by making AIC the lowest. So when you do the step procedure, you're making models, and then you're looking, should I add in a variable? How does the step procedure select the variable to input into the model? When the step procedure runs, it looks at the addition of every variable, and it asks, which of these will do what? It says, here's my current AIC, and it says, which of these will here do what? Which is a concept we need to know about AIC. It looks at your current AIC. We should cover that real quickly, and then we'll do Kahoot. We look at our current AIC, and then we say, which of these AICs are the lowest? Does that make sense? And we would say, add in this variable. Next, we look at a model with that variable added in, and then we say, what will lower our AIC the most? And this one will. So guess what we do? We add it in the model. And we keep doing this algorithmically where we keep adding things in. And by the end right here, we see a model with everything in it, and the choice is to do nothing. But who knows, for 1,000 points, it doesn't have to. I think it does not have to preserve model hierarchy. Someone quote me on that. Let's do this. Let's see. I'm pretty sure it doesn't have to. And let's do a theoretical. Let's do this right here. I'm pretty sure it does not have to. Reg subsets does not. Reg subsets does not preserve model hierarchy, because I know I've seen it in output multiple times. It's in the slides. Reg subsets does not. Okay, let's see if it preserved it. Ooh, crazy output. Did it preserve model hierarchy? That's a really good question. Okay. Let me try to find one where it doesn't. No, that's there. I think it might. Num tattoos. No, that's there. I think it does. So good question right there. I'm pretty sure it does preserve model hierarchy. I think that's the way the algorithm works. Well, let me do this. Let me do the backwards, the both selection. Okay. And num tattoos, desired weight, num tattoos, desired weight. What am I noticing right here? I'm trying to see if things that are included in interactions are also included here. And I think it does. And we could look at the end result right here, because if it's preserving model hierarchy, it should not consider removing num tattoos. So if the algorithm is preserving model hierarchy, it should not even consider removing num tattoos. And it is preserving model hierarchy. That is correct. The algorithm did not consider removing the variable by itself. Does that make sense, Morgan, to your question? Confirmed, the step procedure does preserve model hierarchy. It is not considering removing num tattoos. It would consider removing the interaction right here, which we could probably, there it is right there. The interaction was considered for removing, but it did not. And also, if you look at the start of the algorithm, it doesn't consider interactions. Let me remove output. I remember this now. If you look at the start of the algorithm doesn't consider interactions till it has a variable in there. So also the start of the algorithm also confirms that it is preserving model hierarchy. Now, once again, our friend from overseas brought up a really good point right here, that we have a problem with not just collinearity, but multicollinearity. So how can we investigate the multicollinearity of this? So how could we look into, I thought there was a comment on, maybe I just thought of that in my head. Oh, there it is. However, collinearity is still a problem. Not just collinearity, but multicollinearity. How can we look at the multicollinearity of this? It's one of the last topics we didn't mention, and then everyone get ready for Kahoot. We'll see how many people are playing. How could we look at the multicollinearity of this? What thing are we worried about being inflated? VIF. Yep. Oh, yeah, of course we got VIF. Yeah. Look at, oh, wait, that's not our. Oh, that's got some multicollinearity. Oh, that's got some multicollinearity. And usually you'll see it on the interaction terms. Of course we have a VIF. We got some variance inflation factor. Yes. I love it that you do statistics for medical, and what you ask and what you say is like, and I mean this, and I want people to hear this if you're watching this right now, because we have someone in the medical industry right now who likes to watch and participate, and we appreciate that. Is what we're doing here what is used in industry, like the topics we're talking about, the multicollinearity, the selection of models, the Aka-Ike's information criteria. Do you see these things throughout industry? The idea of model hierarchy, these concepts, these terms that we need to understand and know and be able to communicate what these ideas are, and how we preserve model hierarchy, what variance inflation is. Variance inflation is when your X's bring redundant information to the model. It's correlation of the X's, the way in which your X's explain your X's. This is a bad thing. This means your model is getting the same sort of ideas from the X's. This desired weight gender interaction is bringing tons of redundant information. Now, variance is standard error squared. So can anyone tell me, I love this one, the estimate of desired weight number of piercings? This would be a great test question. Its standard error has probably been inflated about how much? So there's a question I could write for the test pretty quickly. The estimate, or the uncertainty, I should say, the uncertainty, the standard error has been inflated about this much. Very simple number to enter into the chat. The standard error for this coefficient right here has been inflated about this much, which means we have about this much more uncertainty. Now, I'm not saying variance, I'm saying standard error, because standard error squared is variance. So how would you take from the variance and find the standard error inflation? Now, I chose that one for a reason, because it's very close to a number that I can do like that. Who knows, for 1,000 points again? Take a moment, then we're going to do Kahoot next. Who knows what the variance, the standard error inflation is? Oh, Alexander! And Morgan, great job. Yes, KP, you got it. 1,000 points, you got it. Because variance inflation, great job. And thank you so much, everyone practicing. We're going to do Kahoot here in a moment. But variance inflation, we usually talk about standard error. So to go from variance to standard error, because these are the same, like those are the same. But if you want, you could just square root it, and then you're going to get the standard error inflation, and that's going to be the square root of the variance inflation, like mathematically speaking. Yeah, it's for all intents and purposes, we would put a plus or minus on this, like there it is right there. Yeah, so we'd probably put a plus or minus a 0.2 or some 0.1. Like it's about 10. Like about 10 is the answer. It's 9.98, so about 10. Great job right there and great work, people following along. Okay, with that, tell people Kahoot. I think Dr. Brian might be doing her thing. Let me head over to the main screen. Okay, let's put a thing in the chat. I'm gonna head over here to. Oh, hey. Let's go to the Discord. Oh, Discord's closed. Tell people Kahoot's starting up. Okay. Kahoot's in 3 minutes. There we go. So let's put a timestamp in here. Kahoot in 3 minutes. Discord, yes. We have all the Discords. So you have to have a UTK account. I'm sorry. It's UTK account. It's connected to UT. With that, let me get the Kahoot up and going. You can play the Kahoot though. If you win, I'll throw an extra $10 for one of the students. Because I don't know how to send things overseas. What the heck? There's a summit? What? That's interesting. Kahoot is getting big. I got my Kahoot Premium. Star Wars Kahoot. That sounds fun. Where's my Kahoots? Let's see. One more song. How to join? I'll have it up here in just a second. Awesome. Some Bitcoin. Gia, good to see you here. You're welcome, Katie. Good to see you here, Katie. Yeah, people might be joining here from the Discord. Yeah, we haven't listened to it. No, I'm gonna play one of the ones. We got songs we don't listen to as much. Oh, we're here. Gotta change this. Last semester, I actually reached out to someone on TikTok. Where's my edit on this? I have to edit a question because it wouldn't make sense. All right. Saved, done. Is it? Okay, cool. Almost right, everyone. Can I get this one? Yeah, this is chill music. I really like this one a lot. Let me see if I can fix. Why is my Stream Deck being weird? Let me fix the ability to disappear. Okay, so I'm gonna fix this live. Okay. I'll be back here in just a second. I'm fixing this. Okay. Can you guys hear me now? Wow. Don't do that again. Did the screen go black? It said constant bitrate overload. I changed the profile to like... Yeah, let me see if I can get myself back. I don't know what happened. You're not going to be able to see me like here 2 seconds. Okay, I do not know. I do not know why the thing is not working. I'll have to fix it at another time, but I can't get the Stream Deck to do the right thing. So I'm gonna have to like duck out of the way for some of the questions. So bear with me here as I duck out of the way, but I cannot. The Stream Deck is something weird. I don't understand. I reset the computer and Stream Deck doesn't want to interact, so maybe I'll reset it again later, but midstream we can't do it. So let's get the Kahoot going. Thank you everyone for bearing with it right there. Kahoot starting here in just a second. Code about to appear on the screen. Timestamp in. Let's do this. Classic mode. One of these days we should do teams. Here we go. Kahoot on the screen. I might have to disappear maybe the whole time. It's better if I'm on the screen. Okay, there's the Kahoot. Oh, it's new music. Hopefully I didn't just click someone out of here. Oh, is there an... Was that what it said at the start? Is there an update, Alex, to the Stream Deck? I've never heard this one. I don't know if I can update it right now. Listen to some NASA. Alright, maybe this will fix it. Okay, 2 seconds. Let's go to the main screen real quick. I'm just installing the update here. Did Alex fix it? Oh, yeah. I'll be right. We're going to get there in just a half second, everyone. Yeah, it had the Stream Deck off when I started, which is weird. Oh, you see that like blink? Oh my gosh. This is a bad idea. If we crash, it's my fault. I have to shut it down. Alright. So I have to do it later. Oh, geez. Oh, this is a bad idea. Oh no. You can hear me, right? Two seconds, everybody. Can you hear me now? You can hear me now. 2 seconds. I'm gonna bring myself in here. I can actually fix this manually. There we go. So just... Alright. It's gonna change my setup, but I can do it manually now. There we go. Everything's right with the world. Try to update stuff during live streams. Don't do that. I don't know what. Yeah, I guess it's the update or something weird. But I do have control over it now. It's not on the stream deck though. But hey, it's the end of the stream, so we'll get this all fixed up. I'll check it out later. Thank you, Alex, right there. I can't do the points either right now manually. Okay. Who's ready to Kahoot? We only got 10 people here. Your probability of winning a prize is 30%. 30. Oh, we lost a person. We're starting in 20 seconds. Tell people it's time. Is anyone ready to Kahoot in the chat? Who's ready to Kahoot? We got to put on our real Kahoot music. The real Kahoot music. Disco is always what we do right here. We're starting in 15 seconds. 15. I can't even do my timers now. Timers are broken. Everything's broken. 9 people. 10 people. 11 people. Starting in 5 seconds. Leanne, good to see you here. Starting in 5, 4, 3, 2. Someone's going to join in. 1. Let's Kahoot. Here we go. Okay, and I can disappear again. Woo! Okay, we have the first question on the Kahoot right here. If someone wants to predict views, how many views someone gets on YouTube, what model would they use? If someone wants to predict how many views somebody gets on YouTube, what model would they use? So think about the code right here that you'd be writing. You'd be writing msaveinto with a left arrow. You'd be doing lm, and then the y variable, it would be the linear model. So what about if we want to predict, will our video go viral? Like a yes or no. Like maybe we'll define viral as getting like 1 million views. If we want to predict, will our video go viral? Yes, no. What model would we use here? We want to predict, will our video go viral? What model would you use for that to contrast this? Will our video go viral would be a what model? Will our video go viral and get 1 million views? Logistic, that's going to be a yes, no right here. Logistic. The reason to this one for it being views, being quantitative, that is a linear model. Indicator variables deal with the X's. Those are when you have X's, they make indicators for categorical X's. And levels of interest are what we would be predicting. Will our video go viral? Yes. That is in logistic. There's a level of interest and it's last alphabetically. Who's in the lead? Glowing Frog. Great work. No bunnies on this one, but Diplomatic Duck. That sounds like a show, Diplomatic Duck. Continuing on to the next question. What is the typical miss the model makes? We actually didn't mention this the whole time. Sorry, I can't zoom in so well. Make sure to be close to your screen to see what is the typical miss the model makes. Your eyes should immediately be drawing your attention to what? Now think about this conceptually. This concept, great job. Oh, that gets a perfect answers. So when you think about this, it makes it so big now, right? The residual standard error is our uncertainty in the residuals. What is the abbreviation we usually think of residual standard error going by, which is the uncertainty in the residuals? Standard error being uncertainty, residuals being how much we miss by. So miss of the model, the typical. We usually think of residual standard error as a 4-letter word, the RMSE, but the R and the S cancel out, leaving standard error, or excuse me, mean error. Root mean squared error. Now, the reason we square it is because the residuals are positive and negative. We take the mean of that, and then we root it to bring it back to units of the problem. So theoretically speaking, and there are other alternatives like MAE, MAPE, MAC, or mean absolute squared error. No, mean absolute scale error. There's so many, but we like some RMSE here. That's what we do. Who's in the lead is Glowing Frog. Oh my gosh, this leaderboard is just a horse race right here. Everyone, you thought the Kentucky Derby was interesting. This is the real race between Glowing Frog and Gentle Horse, the winner of the Kentucky Derby. Continuing on to the next question. Here we go. When predicting a categorical Y, which will be the level of interest? This is great review. In logistic, the level of is in logistic. Oh no! We've been reviewing this a lot today, so make sure to check it out. In logistic, the level of interest is last. We're talking about a Y variable, and the Y variable is logistic. It's when the Y variable is categorical. And so the first alphabetical is going to be for what? The first alphabetical is the what for when X's are what. So the first alphabetical is for blank when blanks are blank. That is, it's for reference levels. It's for reference levels. And reference levels are for when we have categorical X's and we have indicators to compare them to, right? So the reference level, level, not quantitative Y, level of interest is for a categorical Y. Does that make sense? The level of interest is the last alphabetical when you have a categorical Y. Reference levels are the first alphabetical when you have categorical X's to compare them to indicators. We've done a lot. If you watched today's videos from earlier, we did a lot of practice and review of indicators versus levels of interest. And remember, this is when we're talking about a reference level being the first or a level of interest being the last. And please ask questions as we do this. Good work and good practice. So we pause on the ones people miss more. So, and always ask questions if you have them. Going on here to the next one. Oh my gosh, shakeup of the leaderboard, but Glowing Frog is back right here. Can they keep the lead from Gentle Horse or Super Lemming? Super Lemming. That was a lemur. Let's find out. What is the proper slope interpretation? Oh, reference level first. I like that, Terry. Reference first. Hey, Terry, how did I not figure that out? Terry just getting around 1,000 points. Terry, great work right there and great comments. Yes. So when we do this right here, two individuals that differ in their blank by blank are expected to differ by blank. The full interpretation would be we're predicting height. Oh, no, we're predicting GPA. This question, you can't do so much. Good job right there. Make sure to click the live button if I'm behind. Go down there and there's a live button so you can catch up and be live right there, Alex. So click live. Click live. There's a live button that you can actually rewind the stream if you want. So make sure to click live and there you go. Reference first, logistic last. I don't know, Terry's got some great stuff right there. Two individuals that differ in their weight by 1 pound are expected to differ in their GPA by 0.0037 points, where the individual with the higher weight is expected, not will, expected to have a lower GPA. Once again, and try writing it. That's the way to get the real practice. Two individuals that differ in their weight by 1 pound are expected to differ in their GPA. That's the Y variable. It doesn't say it, but it is. Expected to differ in their GPA by 0.0037 GPA points, where the individual with the higher weight is expected to have a lower GPA. And you can add the negative if you want, but by saying expected to have a lower, we are talking negative coefficient. Whoo! This leaderboard is close. Who's gonna win? Let's find out next. How many assumptions do we fail? Watch out for the trick. How many assumptions do we fail? This one is tricky. This one is tricky. Somebody's going to get it wrong and be like, no! No! Someone's going to lose their streak on this. It is a little subjective, I do admit, but there's only really 3 assumptions here. There's only really 3. There's only 3 assumptions, and we failed 2 of them. Why? It's a little tricky. This is a simple model right here, right? How many X's are in this model? How many X's are in this model? It's a simple model, which gives the answer of how many X's are in it. This, I don't know if I'd love this as a test question, but it's kind of what we should know, and a lot of people got this right. So we're looking to see... Equal spread is great. So we don't fail that one. Equal spread, yeah, equal spread. So there's 1 X in this model. So here's the thing. The linearity of weight is the linearity of the overall model. This is the same condition. This is redundant. In the multiple model, the overall model has its own p-value. So technically, we are failing the linearity of the X, which is the model. Does everyone see this is the same condition? And that only applies for the simple world. That's why whatever p-value you see for this X, well, the X is what makes the model. So the linearity of the X is the linearity of the model. So that's 1 fail, and then the normality fails. We're good on equal spread right there. So we pass the equal spread. We fail on 2 conditions. Little tricky right there. There are 3 p-values below. I don't think I have any other big trick questions on here, but who lost their streak? Oh my gosh. Gentle Horse still running away with it, but you never know. Majestic Unicorn and Glowing Frog still there with Bright Eagle and Super Lemming. Let's find out what happens next. Here we go. True or false, if we fail the test with p-values, we can't use the regression model. And our friend was bringing this up a moment ago, talking about, well, wait, if we fail these tests, a lot of times that happens for larger sample sizes. If we fail the test, we can't use the regression model. So if you say true, you're like, you can't use it, Brian. Throw it out. It's gone. Who wants to explain if we fail the test, what do we do? If you fail the test and your sample size is greater than 25, you do what? If you fail the test and you have a large enough sample size, you would then do what? If you fail the tests, so we failed some tests, right? We said, we failed that one, we failed this one, but our sample size is larger than 25. We now do what to see if we can use it? To see if maybe we can use it. We were doing this a little while ago. Check this section of the video. We check the plots. We look at the residual plots to see how bad did we fail. And really great comments that, and once again, that's the application in industry you're hearing from them, is that when you have a large sample size, you're probably going to fail because all models are wrong. Some are useful. So we're checking the plots to see, even though our model's wrong, which all models are, we're going to then see, is our model of any use? How bad is it? So we then look at the plots to see, well, how bad did we fail these conditions? So false, we can still use it. It's how bad did we fail? And remember, don't worry if you win the Kahoot. One of the big reasons to play the Kahoot is just to practice. So be here practicing, see what you get, see what you need to write down, have your cheat sheet out with you. Great job, Gentle Horse, Super Limmer, Bright Eagle, Glowing Fox, and Dynamic Mouse. First time on the leaderboard. Congrats, Dynamic Mouse. Question number 7. Which assumptions can be checked using a QQ plot? So which one of these is a QQ plot? The first plot here is the predicted versus the residuals. That's a scatter plot showing you it. This is a histogram. We know what we say in our class, no looky at the histogram, and that is a QQ plot. QQ plots are the quantile plot. That's what the QQ stands for, quantile. Oh no, Alex, you're all good. It's the third plot right here. Is the quantile. Shreya, great to see you here. And it is the normality. So a lot of people often think that this is linearity. No, that's the line, and the line has been flattened out to 0. This is the linearity, whether the points are around it or not, like in a proper linear sense, which it's decent. This is the normality of residuals, which we use a line to tell us if it follows the normal curve. We're not checking linearity here. This is a normal curve. It's literally taking this thing right here and showing you it as a line, and look where the big deviation is. It's down here. Now, no looking at histogram. There's a big deviation of normality on the low side, also seen right here. You can kind of connect these points are there and there and there right there. So you can connect the ideas to say there's a problem down here, and we don't want to see things deviating from the red line on the QQ plot for normality. Good job right there. Continuing on further, it is doing quite well. Quick Hamster, good to see you here. We hope you enjoy the show, even if you're just here for a while. Which plot checks the equal spread? The first, the second, the third, or none of these? Which plot are we looking at here for the equal spread? Which plot is the equal spread one? Is it that first one, the second one, or the third? It is the first. What two things do we check? Just a reminder, what two things do we check with this first plot? We can look at the equal spread, and we can also look at the what of the model. Not that over here. The first one, we can look at equal spread and what else? The first plot, we can look at the equal spread and what else? What can we look at there? We can look at the equal spread and what else? Well, the equal spread is the vertical spread, which seems kind of consistent. That's the equal spread is the vertical spread. That's right, Gia. Great answers. And the linearity. So the two things you're looking at right here when you're looking at that plot is you are looking at the equal spread, which is going to be this right here, which is decent for the most part. I mean, within that. And then the second thing you're looking at here is the linearity, is if the line goes through the data. Great job, Leanne, right there. And then over here is where you look at the normality, and it even says it down there. This is the normality. So you've got your three conditions. We have the equal spread of the residuals, we have the linearity of the model, and we also have the normality of the residuals. All three conditions shown up right here. Here, I'll disappear so you can see what I circled. That literally says the checking of the normality right there. So make sure to know how to look at a check residuals right there, and that's good. Who's in the lead? Quick Hamster quickly jumping up the leaderboard. Got a little bit of ground to make up on Glowing Frog, Gentle Horse, and Super Lemming. Here we go next. Multi-select. Multicollinearity is what? I hope I put in right answers. Invalidates our model. does not invalidate the model. Is shared variation in the y's, is shared variation in the x's. So it's kind of neat. You got some dichotomous choices right here. Who's going to get all the points? Multicollinearity is when redundant information is brought by your x's, and we still can use our model. So it does not invalidate our model. We can still use it. That's what I mean by does not invalidate. You can still use your model. You don't like it. It just adds more what to your estimates. Multicollinearity will increase your what in your estimates. Hence, variance inflation, which we were just talking about standard error a moment ago. It's going to increase the what for your estimates of your x's. You're going to have more what in your estimates because they're bringing redundant information. It's like when you invite all your friends to your party and they all bring pizza. You're like, oh, dang it. Now I'm confused. I don't know what friends. You're going to have more uncertainty in your estimates. You're going to have a higher standard error, and we don't like that. We don't really like it in descriptive models because that's where the coefficients are most important. So if you have redundancy in your x's, shared variation redundancy, it doesn't invalidate your model. Really just, it's not good. We don't like it. We don't like shared variation in our x's. We want our x's to bring unique information. So good right there. Woo! Bright Eagle. We got a first, second, third place right here. Next question. Here we go. Great job, Bright Eagle. All models are wrong. I've been saying this about 20 times today. I'm going to feel so sad if someone gets this wrong. Please. There are some ridiculous answers on here. This is like one of my favorite questions I ever wrote. I don't think... We put the quote on the test. I think it is in some of the question banks. I think. I know, right? If you've heard me say this quote a billion times, it's how statistics work. It's funny, I was watching a YouTube channel and I commented, I was like, well, all models are wrong. And they were like, yep, but some are useful. Don't worry if you got it wrong. Don't worry. Great job, everyone. Don't worry if you're the one person who got it wrong. That's totally fine. We're going to give 1,000 points. I paid someone to get it wrong. All models are wrong. Some are useful. If I get this wrong, my whole attendance... That's awesome, Gia. So all models are wrong just means we're trying to do math to explain the world. We're not doing some E equals MC squared right here in statistics. We're doing some, I'm going to predict your body fat when you tell me 5 things. We're kind of that person who really loves to guess stuff. But we're better at guessing things than just taking random guesses. We use variables that actually have non-random relationships, hence what we do with p-values and stuff, to find out significant ways to explain things. But it's based on sample data, which just makes estimates. So all of our models are not the truth, but some of them can be really useful. And that goes to practical significance, whether or not they're useful. Are they practically significant? Maybe. Maybe. Great job. Leaderboard's locked up. Continue on to the next question. Here we go. When would we be extrapolating with the following model? So extrapolation applies to the what variable. I like it. We've covered a lot of things we haven't talked about lately here, but extrapolation applies to the what variable. Extrapolation applies to the what variable. You can answer that in the chat if you want, but extrapolation only applies to the what variable. Extrapolation only applies to making predictions. Now that's a Y thing. But when we make predictions outside the x-axis, can't even speak. Ooh. Oh, wow. Why is now a lot of people answered, people said horsepower, that's horsepower 500. That is a Y. So that's not the idea of extrapolation. It only applies. Now I want you to take a look. Why, and a lot of people said weight of 5. Why is weight of 5 not an extrapolation of the model? So we got to pause here. Extrapolation only applies to x's. And why is a weight of 5 not an extrapolation of the model? Extrapolation good job. You're the one person who got a weight of 5 is contained within the boundaries of the data points. Does that make sense? Great job, Alex, right there. There is a data point above it. So this is the X space right here. So this is the X space. And when are we extrapolating? We are extrapolating. So now this is extrapolation over here. So extrapolation. we're extrapolating, which 1 is down here. Extrapolation occurs outside the X, and Terry, great job of reiterating, outside the X boundaries. So 1 is not contained within the boundary of the X's, and thus it would be an extrapolation of our model. So anything inside the X space is not an extrapolation. The Y predictions are just what they are. Extrapolation is only concerned with the X variable and when we make predictions. No worries, Alex. Hey, Alex, great job right here. We're going to throw you, I got to click. We're going to throw you another 1,000 points. People are like, yes, we love all those points because got to get that bonus before the end of class here. So please just keep giving it a shot. Keep remembering. And if you get it wrong, that means you were here to learn and you got something more than just the points. Going on to the next question right here, we'll see. Leaderboard got it wrong. Someone got it right who's not on the leaderboard. Woo! Who got that right? Good job. You got it right. Congratulations. Going on to the next question. Here we go. Multi-select. Model hierarchy requires which of the following? Categorical X's have all indicators included. Interactions have components of the interaction in the model. The intercept is included in the model. Polynomial terms have lower polynomial terms. I mentioned all of these but one during our review, and I mentioned 3 things. It is true for the last one. I didn't mention it. It's not used quite often, but it is true that if you're making a model, you need to include the intercept. Thought that might get a few people. It is true. It's in the model building slides. We go over that you have to include the intercept. But if you remove the intercept, that is checked behind me right there. It's checked over there too. But the intercept is part of your model hierarchy. I'm not a big fan of removing it because you're destroying model hierarchy and the intercept's created for a reason. But you can remove the intercept. And that would be harming model hierarchy. Check out earlier today where we go through a big detailed description of model hierarchy and review what it is and how we preserve model hierarchy. It's basically including the components that build up to these things, in short. So big, leaderboard's going crazy. What are polynomial terms? Those are the ideas of squared variables. Let me bring up the notes we took on that earlier. A polynomial term, here it is right here, is when you have like x to the 3rd power, and then an interaction is multiplying them. And then we did another tab right here where we talked about the inclusion of all the indicators. It is true, though, that including the intercept is what is needed to preserve model hierarchy. We didn't mention that here. I'm just not a big fan of removing the intercept, but that is a true fact. If you remove the intercept, and it is in the model hierarchy notes, so it was mentioned during class too. It wasn't mentioned during today's review, though. You're welcome, Alex. Keep up the good questions. And now the next question is, how do we select models based on AIC? Let me get out of here. What's a good AIC? Models, we use AIC to compare models. So what's a good AIC? You'd be like, oh man, that's an awesome AIC. What is a good AIC? Everyone knows right there. Some lowest AIC. The lower the AIC, the better. What's the best AIC? Just repeat again in the chat. Another yes. Oh, Shreya, yes, with like 475, 474, all this good stuff. We don't forget about some AIC. AIC, AKEK's information criteria. The lower the AIC, the better, and it can go to negative infinity and beyond. Not quite negative infinity, but it goes to negative infinity, and it approaches that as our model gets a sums of squared error of 0, which is an R squared of 1. So negative or lower AIC, the better. Lowest, Shreya knows that right there. Shreya, 1,000 points for playing along and helping out right here and getting some practice. These concepts are used throughout all of our classes, so they build. Next question. Ooh, leaderboard's locked up. Gentle Horse, can you hang on to it? Well, you got a pretty good lead, so maybe. Let's find out right here. Next question is multi-select. Got so many multi-selects. Which of the following are true about R squared adjusted? Ooh, we didn't mention R squared adjusted. So which of these can be true? Oh, I tried getting in, but still. Oh, no worries. Hope to see you there. You got it. Which of these is true? Yeah, Kahoots are so much fun. Which of these are true? So only one of them is not true. And the only one that is not true is that it can be over 1. I'm trying to bring the volume down a little bit. Is that it can be over 1. R squared adjusted can be negative because it's R squared with a penalty term. So think about this. If it's R squared with a penalty term, what's the lowest R squared? Just tell me, what is the lowest r squared you can get? The worst r squared is what? Let's type it in the chat. The worst r squared. It's a good way to remember. It's like, okay, the worst r squared I can get is what? What is the worst r squared? Not negative, 0, 0. Because that's 0% of your variation explained. Good work right there, and keep up those answers coming. So 0, does that make sense? 0. And that would mean none of the variations explained. So think about this. If we penalize ourselves, which means we're going to subtract off of it, then what is even worse than 0? A what number for r squared? Because 0 is the worst r squared adjusted is a penalized r squared. So if we're going to penalize ourselves and we're at 0, r squared adjusted can be negative. Now it can be negative, and it can get ridiculous negative, not just even -1. You can get an r squared adjusted of like -40 or something. You can just get insane r squared adjusted. So r squared adjusted really has no, if it's negative, it's just horrible. It's really bad. If you get a negative r squared adjusted, that's really bad, because then you would then use that to do what? What do you think you would then use that r squared adjusted to do? Because you could then look at it and be like, should I use this model or this model? Your goal in using the r squared adjusted is why? Why would you use r squared adjusted? You'd use it to compare models, to compare. And think about this. Why do we use r squared adjusted? Which of these models has more of an advantage? A model with one variable in it, or a model with 1,000,000 variables in it? Which of those models has more of an advantage? And Alexander's saying it right. The model with 1,000,000 variables has an advantage, right? It's got a bunch more variables, but it's going to get a higher penalty for having more variables. If you were to play somebody in Smash Bros, and you've only played one game ever, who has more of an advantage? The person who's played one game or the person who's played 1,000 games of Smash Bros? We're talking some Smash Bros here. Who has more of an advantage? The person who's played one game or the person who's played 1,000 games? The person who's played 1,000 game, right? Because they've played more. They have more X's. They have more experience. And so with the extra, we use what's called r squared adjusted to, as Alexander said, level the playing field. So the r squared adjusted is a fair way. The guy who picks hero. I mean, I main Samus, so got to deal with some Samus right there. More X's in your model will always increase your what? To review again, more X's in your model will always increase your what? More X's, and if it's the same as X's especially, will always increase your what? More X's will always increase your what? More X's will always increase your what? You have a model, you put another X in it, and the X gets something, it'll always increase the r squared. So why do we have r squared adjusted? Because it won't increase r squared adjusted, it'll increase the r squared. We have r squared adjusted because if we're putting in more X's, we actually get more of a penalty. And that's what r squared adjusted is it's the penalized r squared. Does that make sense why this exists? Great work with their Shreya. Excellent work. We're going to throw out another 1,000 points. We got crazy today, but Shreya and everyone, keep up the great work in the review. R squared adjusted is the penalized one where putting in more variables can lower it. It doesn't have to lower it, but it can. You just get more penalty. If the variable's really great, it'll be awesome. For one more 1,000 points, what other model comparison metric do we have, which is an alternative to r squared adjusted? What other model comparison metric do we have that we were just talking about a moment ago, which is used a lot more in other classes, that we also have to compare models? Because r squared adjusted can be used to fairly compare models, but what's another model comparison metric that we can use to fairly compare models? What is another for 1,000 points? I'll take RMSE. That is correct, KP right there, and AIC. AIC is a model comparison metric, how close we are to the truth. Within 2 is about the same. Within 10 is pretty different. Within 10 to 2 is like, I don't know. And then RMSE is the typical miss the model makes. RMSE, AIC, and r squared adjusted are pretty fair ways to compare models, and they all have penalty terms in them for more variables in a model. So RMSE can also be used to fairly compare models in the multiple world. That is a correct answer right there. Great job. 2,000 points. All those answers. Continuing on. Bright Eagle in a 3rd place. Who's going to win? Someone creates a regression model using months of the year. How many indicators? You got this. I trust you. I trust you. Someone creates a regression model using months of the year. How many indicators? I should have edited in like a 32 for the memes. So how do we know how many indicators there'll be? Indicators are for categorical X's, and indicators are, great job, not too much to review. There's 12 months of the year. Subtract 1, you get 11. 1 month of the year is the reference month. 1 month, January, February, March, April, May, February, March, April, May, June, July, August, October, November, December. What month of the year is the reference month, which by default we'd compare all of the months to? January, February, March, April, May. Oh, June, July. Again, months of the year. April, because it's the first. Reference first. Reference first. Reference first. So it's first alphabetical, not first month of the year. Not January. Good review. Next question. Adorable turtle. Oh, so good. Next question. You're doing a great job, adorable turtle. What does the following p-value represent? Ooh, that's a toughie. What does it represent? So you should be able to identify what this comes from. And yeah, a little tricky. The p-value is 0.02 if you can't read it. That p-value is in a check regression output. Sorry, it's a little small. I usually try to zoom in on these. That p-value is in a check regression, and the p-value is low, so we fail the test of linearity. New information goes to the summary, and then we fail it because the p-value is low. You do not want to see low p-values in check regression. Also, check out the video today. We did a big thing on check regression for logistic and for linear models. If you're reviewing, if you have the test a little bit later than today. Next question right here. Let's do it. Gentle Horse has galloped into the lead, but it's a close call between Bright Eagle and Glowing Frog. Let's check it out. Last question. The following model is predicting if someone will purchase with 3 visits. What is the probability of purchasing? Uh-oh. Hopefully we have 60 seconds. We do. You can actually get it super quick. Someone's like, do I want to risk it between 2 answers? How can you narrow this down pretty quickly to know if you've gotten it correct? We should understand theory on what we're doing. So how can you narrow this down super quickly to 2 answers? If we're predicting probability with logistic, then the answer must be what? If you've answered, feel free to join in the chat and say like, oh, I have to narrow it down to this. And this goes to Alex. If you get this, you got it great. You might have guessed it, but see if you get the answer. And actually, if you remember from predicting Brian's height earlier, we got like 4.5. Oh, yeah. So you probably were between 2. Now, remember, earlier, good job. Okay, so people... Ooh, wait. What happened here? What should your answer be between? Everyone remind me before we go to the winning screen right here. When you do logistic, all your answers need to be between what and what? When you do logistic, all your answers need to be what? When you predict probabilities... This is a big thing. When you do logistic and you predict probabilities, all your answers need to be what? All your answers need to be what? When you do logistic and predict probabilities, every answer you get for your final answer needs to be between 0 and 1. 0 and 1. For 5,000 points to end the Kahoot, who can type the equation in the chat that gets us the correct answer? I'm not going to solve for you. I want to see. We did this a lot. We did a whole section earlier on... we did this section right here, predicting Y with logistic. So I'll put these timestamps in the video in just a moment right here after the video ends. We did this section right here, but who can tell us the equation to solve? And I'll put it in here. But who can tell us the equation to solve? And then we'll go to the winning screen. So that is it. And then Morgan, what do you plug in there? So Morgan, you've got it. You've got the 5,000 points for everybody. But tell us, what do we plug in for Y? There we go. Alexander's showing it too. Great job, everyone doing it right here. Y was 6. Well, when we solve it. So when you solve the equation, you get 6. And then there is... Oh, we're missing a parentheses, I think. There it is right there. So we're missing one more parentheses on that. You can actually append the parentheses. But e raised to the 6 over 1 plus e raised to the 6. And the reason we're getting 6 right here is because the equation was logit of y is equal to 0 plus 2 times x. And it said in the question we had x equal to 3 visits. So a really kind of small question, but you're plugging in 3 right here, times it by 2, getting 6. And then that value right there. And if this is a little quick, We go through a lot of examples today. Let me ask you this. Did anyone learn a lot better how to solve logistic and maybe got this problem right here? Did anyone learn a good bit better? Because we did a whole section, 17 minutes there, and we also did some at first. I hope someone is like, yes, I can solve logistic now. It's e raised to the over 1 plus e raised to the. And we were solving that earlier. Good job, Alex. Yeah, Alex, we're throwing 5,000 more. Alex, I hope you do a great job. I think you might be in another section, but Alex, congrats to you, Alex. You've been here this whole time. I hope you've had a great time. Hope you enjoyed yourself at this review. So great job, Alex, and shout outs to everyone right here answering the questions, participating. But you know what it is. It is time for the winners of the Kahoots. And it's not me who wins the Kahoots, or who says the winners. You know who says it.
Is it? Not me, but it's Tiny.
Not me. It's not Mega Brian. It's Tiny Brian.
Tiny Brian, there we go. Tiny Brian. Woo! Tiny Brian here. Really tiny Brian. Okay, let's do this. Where's the Kahoot winner screen? You're welcome, Terry. Tiny Brian. Wait, where is it? Tiny Brian. Okay, here. Oh my god, that's not gonna work. I'm too tiny. Okay, regular Brian. There we go. Tiny Brian here. Okay, the winner of the Kahoot is, you know who it's gonna be. That's third place, Glowing Frog. Yeah, great job, Glowing Frog. Second place, Bright Eagle. Good job, Bright Eagle. And you know who's gonna win. It is the horse, the number 1, Gentle Horse. Great job. Tiny Brian.
Getting more normal. Now I don't sound so normal, though.
Tiny Brian.
There we go. Okay, there we go. Tiny Brian won't be happy if I change his voice. That I had to impersonate Tiny Brian for this one. An impersonation of Tiny Brian. There we go. Awesome work. Great job, everybody. I'm going to throw in the timestamps. So give me a quick second. I'll forget if I go away. I'm going to have to reset the computer, throw in the timestamps, fix the stream deck. So many things going on. Congratulations to everybody. Really great review today. Good practice. Yeah, thank you. And thank you, Terry, for swinging by. Shouts to everyone right here. I misspell hierarchy, apparently, but the timestamps are now in the video. You can come back and watch this at any time. But we'll hop over to the main screen. We'll say bye. You're welcome, KP. You're welcome, Alyssa. Welcome, Alexander. Thank you, Shreya. Thank you, Terry. Head over here to the main screen. Where's my background? I have no stream deck options. I'm going to be on here twice. Hopefully that didn't change. Thank you so much, Terry. I can't even play any music. I guess go. Here, we'll play ourselves out. You ready? We have to get some music. I put up 2. Sometimes piano sounds I don't like. The green screen's breaking, everything's breaking, we're breaking reality.